There is a world that exists just beyond the edge of what the eye can see. A realm so small that 1,000,000 of its structures could rest on the head of a pin. And in this invisible landscape, in this territory measured in billionths of a meter, something extraordinary unfolds. The nanoscale, a dimension where atoms dance and molecules arrange themselves into patterns of astonishing complexity, where the familiar laws of the everyday world begin to bend and shift, revealing properties that seem almost magical in their strangeness. Imagine standing at the threshold of perception, peering down through layer after layer of magnification, past the grain of sand, past the living cell, past even the tiniest bacteria, until matter itself begins to reveal its most intimate architecture. This is where nanotechnology lives, in the spaces between what we know and what we are only beginning to understand. The word itself carries a kind of music. Nano, from the Greek word for dwarf, meaning 1/billionth, a scale so diminutive that it challenges the imagination. Yet it is here, in this realm of the infinitesimal, that some of the most profound transformations of our time are taking place. To speak of a nanometer is to speak of a measurement almost beyond comprehension. 1/billionth of a meter, roughly the width of 3 or 4 atoms placed side by side. A human hair, by comparison, stretches about 80,000 nanometers across. A red blood cell measures some 7,000 nanometers in diameter, and a single strand of DNA, that elegant spiral staircase that carries the blueprint of life, is only about 2 nanometers wide. At this scale, matter behaves differently. Gold, which appears lustrous and yellow in the world we inhabit, can take on hues of red or purple when crafted into nanoparticles. Materials that are opaque can become transparent. Substances that conduct electricity in bulk form may become insulators, or vice versa. The rules change, and in that changing, new possibilities emerge. The story of nanotechnology is not merely a story of making things smaller, though that is part of it. It is a story of discovering that smallness itself unlocks new properties, new behaviors, new ways of interacting with the physical world. It is the realization that when we work at the scale of individual molecules and atoms, we can engineer matter with a precision that borders on the miraculous. Long before the term nanotechnology entered our vocabulary, nature had already mastered this domain. The lotus leaf, for instance, repels water through nanoscale structures on its surface, creating what scientists would later call the lotus effect. The wings of certain butterflies shimmer with iridescent colors produced not by pigments, but by nanoscale architectures that bend and scatter light in precise ways. Even the gecko's remarkable ability to walk up walls comes from millions of nanoscale hairs on its feet, each one creating a weak molecular attraction that, when multiplied, grants astonishing adhesive power. These examples from the natural world whisper of what becomes possible when structure is controlled at the molecular level, and humanity, in its endless curiosity, has learned to listen. The journey into this small world required new tools, new ways of seeing, because at the nanoscale, ordinary microscopes fail. Light itself, with its wavelengths measured in hundreds of nanometers, cannot resolve features smaller than its own waves. It would be like trying to feel the texture of silk while wearing thick winter gloves. So new instruments were imagined and built, devices that could sense the atomic landscape through other means. Scanning tunneling microscopes that measure quantum tunneling currents between a sharp probe and a surface. Atomic force microscopes that trace topography by feeling the push and pull of atomic forces. These technologies opened a window into a world that had always existed but had remained hidden, waiting. And what was seen through that window transformed everything. The realization dawned that atoms and molecules could be not just observed, but manipulated, arranged, designed, that materials could be built from the bottom up, one atom at a time if necessary, with intention and purpose. This is where the story truly begins, in the meeting place between human ingenuity and the fundamental building blocks of matter, in laboratories and research centers, in moments of insight and years of patient experimentation, in the gradual understanding that the very small could have very large implications for medicine, for electronics, for energy, for the way we understand and interact with the material world. The air in such places hums with a particular kind of quiet intensity. The controlled environments where contamination must be measured in particles per cubic meter. The clean rooms where a single speck of dust would be a mountain. The instruments that vibrate at frequencies imperceptible to human senses, isolating themselves from the tremors of passing footsteps, from the distant rumble of traffic, from anything that might disturb the delicate work of positioning atoms. Here, in these spaces, the future takes shape one molecule at a time, invisible to the naked eye, but profound in its potential. The earliest whispers of this possibility, the first inklings that matter might be controlled at the atomic scale, emerged not from a laboratory but from a lecture hall on a December evening in 1959, when a physicist named Richard Feynman stood before an audience at the California Institute of Technology and delivered a talk with a title both simple and provocative. There's plenty of room at the bottom. Feynman, with his characteristic playfulness and intellectual daring, asked his audience to imagine writing the entire Encyclopedia Britannica on the head of a pin, to consider storing all the world's books in a pamphlet, to envision machines building smaller machines, which would build smaller machines still, descending in scale until individual atoms could be placed with the precision of a typesetter arranging letters on a page. At the time, this vision seemed like science fiction, a charming thought experiment from a brilliant mind. But Feynman was proposing something more concrete. He was suggesting that the laws of physics did not forbid such manipulation, that there was no fundamental barrier preventing humanity from rearranging matter at the molecular level, that the limitations were merely technological, not physical. He spoke of biological systems, of the cell's ability to manufacture complex proteins by reading genetic instructions, of nature's own nanotechnology operating within every living thing. And he wondered aloud why humanity could not learn to do the same, to build molecular machines, to write information at atomic densities, to manufacture materials with atomic precision. The lecture concluded with two challenges, two prizes offered for achievements that seemed fantastical, one for creating an electric motor no larger than 1/64th of an inch on each side, another for writing text small enough that the entire page of a book could be reduced by a factor of 25,000 in linear scale. The first prize was claimed was within months. The second took several more years, but both fell to human ingenuity far sooner than many expected. Yet Feynman's talk, though prescient, did not immediately spark a revolution. It was a seed planted in soil that would need decades to become fertile. The tools did not yet exist. The understanding was incomplete. The vision waited. Through the 1960s and 70s, other streams of thought began to flow toward the same destination. Materials scientists explored the strange properties of very small particles. Chemists synthesized molecules of increasing complexity. Physicists probed the quantum mechanical behavior of nanoscale systems, each discipline moving in its own direction, not yet seeing how the paths would converge. In 1974, a Japanese scientist named Norio Taniguchi used the term nanotechnology for the first time, defining it as the processing of materials by 1 nanometer or less. He was working on precision machining, on the challenge of creating surfaces smooth and precise at scales smaller than ever before achieved. His work was practical, focused on manufacturing and tolerances, on the incremental refinement of existing techniques. But the term he coined would come to mean something larger, something more ambitious. The true transformation began with the invention of new eyes, new ways of perceiving the atomic world. In 1981, at IBM's research laboratory in Zurich, two scientists named Gerd Binnig and Heinrich Rohrer created an instrument unlike any that had come before, the scanning tunneling microscope. This device worked on a principle both elegant and strange. A sharp metal tip, tapered to end in a single atom, was brought so close to a surface that electrons could tunnel between them, a quantum mechanical effect, where particles pass through barriers that classical physics says they cannot cross. By measuring this tunneling current as the tip scanned across a surface, the microscope could map the positions of individual atoms. For the first time in human history, atoms were not merely theoretical constructs or statistical averages. They were visible, countable, real in a way they had never been before. The images produced by the scanning tunneling microscope showed surfaces as landscapes of atomic bumps and valleys, each peak representing a single atom, each contour revealing the underlying structure of matter. Binnig and Rohrer's invention earned them the Nobel Prize in Physics in 1986. But more than that, it opened a door. If atoms could be seen, then perhaps they could be touched, moved, arranged. Just a few years after the scanning tunneling microscope's invention, another instrument joined the toolkit, the atomic force microscope, developed by Binnig along with Calvin Quate and Christoph Gerber. This device measured not electron tunneling, but the tiny forces between atoms using a cantilever, a microscopic diving board with a sharp tip that would bend ever so slightly in response to atomic attractions and repulsions. The atomic force microscope had an advantage. It could work on any material, not just conducting surfaces. It could operate in air, in liquid, in varied environments, and it too could resolve individual atoms, feeling the topography of matter with extraordinary delicacy. These tools transformed nanotechnology from speculation into experimental science. Researchers could now explore the nanoscale directly, mapping surfaces, measuring forces, understanding how matter behaved when confined to dimensions of just a few atoms. And in 1989, a group of scientists at IBM's Almaden Research Center in California demonstrated something that captured imaginations worldwide. They used a scanning tunneling microscope not just to image atoms, but to move them, positioning 35 individual xenon atoms on a nickel surface to spell out the letters IBM, each atom placed with deliberate precision, each one coaxed into position by the microscope's tip. The image became iconic, proof that atomic manipulation was possible, that Feynman's vision of arranging atoms like a typesetter arranging letters was not fantasy but achievable reality. The photograph showed 3 letters formed from glowing dots, each dot a single atom, resting on a surface imaged at a temperature just a few degrees above absolute zero. This was not yet nanotechnology as it would come to be practiced. The work required extreme cold, ultra-high vacuum, hours of painstaking effort to move a handful of atoms. But it was a beginning, a demonstration of principle that would inspire a generation. Around the same time, the concept of nanotechnology was being elaborated in another direction through the visionary and controversial writings of K. Eric Drexler, an engineer and futurist who had studied with pioneers of space systems and molecular biology. Drexler began publishing papers and books that imagined a future of molecular manufacturing, of assemblers that could build virtually anything by arranging atoms in precise patterns. His 1986 book, Engines of Creation, painted a picture both utopian and unsettling. Nanoscale machines that could repair cells, manufacture materials with perfect precision, clean up pollution, even reverse aging, but also machines that could replicate uncontrollably. The famous gray goo scenario, where self-replicating nanobots consume all matter. A nightmare of unintended consequences. Drexler's ideas were speculative, far beyond what any laboratory had achieved, and they sparked intense debate. Some scientists embraced the vision, others criticized it as impossible or dangerously misleading. Arguments erupted over what was physically feasible, over whether molecular assemblers could ever work as Drexler imagined, over whether the promises were premature and the warnings overblown. Yet even amid controversy, Drexler's work served a purpose. It made people think. It raised questions about what nanotechnology could become, about the profound implications of molecular control, about the need for foresight and responsibility as these capabilities developed. It brought nanotechnology into public consciousness, for better and worse, as a field of both extraordinary promise and potential peril. Meanwhile, in laboratories around the world, more modest but tangible progress continued. Chemists synthesized fullerenes, soccer ball-shaped molecules of 60 carbon atoms, discovered accidentally in 1985 and recognized with a Nobel Prize in 1996. These buckyballs, as they came to be called, were purely nanoscale objects, molecular cages with unusual properties, able to trap other atoms inside them, strong yet hollow. Shortly after, carbon nanotubes were identified, cylindrical structures formed by rolling sheets of graphene. These tubes, just a few nanometers in diameter but potentially millimeters long, proved to have remarkable characteristics: stronger than steel, excellent conductors of electricity and heat, lightweight and flexible. They became one of nanotechnology's most studied materials, a building block that seemed to promise countless applications. The late 1980s and early 1990s saw nanotechnology coalesce as a field. Conferences were organized, journals were founded, research groups formed, universities began offering courses. funding agencies started directing resources toward nanoscale science and engineering. What had been scattered insights and isolated experiments began to organize into a discipline, one that drew on physics, chemistry, biology, materials, science, engineering, all converging on this realm of the very small. Governments took notice, recognizing that control of matter at the nanoscale could transform industries, create new economies, shift the balance of technological power. In the United States, the National Nanotechnology Initiative was launched in the year 2000, coordinating research across federal agencies, directing billions of dollars toward fundamental science and technology development. Other nations followed: Japan, European countries, and later China, all investing heavily in nanoscale research, all seeking to position themselves at the forefront of what many believed would be the next industrial revolution. The early years were characterized by exploration, by learning the rules of this unfamiliar territory. Researchers discovered that materials behaved differently at the nanoscale, not as anomalies, but as a matter of course. Quantum effects became important. Surface area relative to volume increased dramatically. Changing chemical reactivity, optical properties, mechanical strength, electrical conductivity, all could be tuned by controlling size and structure. Gold nanoparticles, for instance, could appear red or purple or blue, depending on their size, because the electrons on their surface oscillate collectively when struck by light, a phenomenon called plasmon resonance. And the frequency of that oscillation, the color produced, depends on the particle's dimensions. This meant that color could be engineered at the nanoscale, not through dyes or pigments, but through structure alone. Similarly, titanium dioxide, a white pigment in bulk form, becomes transparent at the nanoscale, but retains its ability to absorb ultraviolet light, making it useful in sunscreens that don't leave a white residue. Zinc oxide, another UV blocker, behaves the same way. These were among the first commercial applications, modest perhaps, but they demonstrated that nanotechnology could move from laboratory curiosity to everyday product. The foundations were being laid, the tools were improving, the understanding was deepening, and the community of researchers was growing, all preparing the ground for what would come next, for the flowering of applications, for the realization of some promises and the recalibration of others, for the movement of nanotechnology from its pioneering phase into something more mature, more complex, more interwoven with the fabric of modern technology and medicine. But that part of the story was still unfolding, still ahead, waiting in the quiet hum of laboratories where invisible architectures were being built, atom by atom, molecule by molecule. The laboratories where this work proceeded had a quality of controlled stillness, spaces designed to eliminate the tremors and vibrations that plague precision at the nanoscale, buildings constructed on foundations isolated from the surrounding earth, floors floating on pneumatic cushions, rooms wrapped in layers of acoustic dampening, all to create an environment where a microscope's probe could be positioned with atomic accuracy. Inside these clean rooms, the air itself was manufactured, filtered thousands of times per hour to remove particles, each breath of atmosphere passing through membranes with pores measured in fractions of a micron, because at the nanoscale, a single speck of dust would be a boulder, A stray fiber from clothing would be a fallen tree. Contamination had to be measured not just in parts per million, but in particles per cubic foot, and the standard was exacting. Class 10 clean rooms allowed no more than 10 particles larger than the half a micron in each cubic foot of air. Researchers entering these spaces underwent transformation rituals, donning suits that covered every surface of skin, hoods and face masks, gloves, shoe covers. The garments themselves were woven from continuous filament polyester because regular fabric sheds no particles with every movement. Even breathing required care, each exhalation potentially releasing moisture and biological contaminants. So the air people breathed out was directed away from sensitive work areas through carefully designed ventilation systems. The work proceeded in this rarefied environment with a patience that bordered on meditative, because manipulating matter at the nanoscale could not be rushed, could not be forced. It required alignment with the fundamental rhythms of atomic interactions, the delicate touch of forces measured in piconewtons, the awareness that quantum mechanics governed every outcome. As the first decade of the 21st century unfolded, nanotechnology began to diversify into distinct streams, each following its own logic, pursuing its own applications, yet all drawing from the same wellspring of nanoscale understanding. In materials science, researchers learned to create nanocomposites, materials that blended nanoparticles or nanostructures into conventional matrices. Adding tiny amounts of carbon nanotubes to polymers could increase strength dramatically. Incorporating nanoscale clay particles could reduce permeability to gases, making better barriers for packaging. Mixing quantum dots into materials could create displays with more vivid colors. Each innovation relying on the principle that nanoscale additives could transform bulk properties in ways that larger particles never could. The sporting goods industry became an early adopter. Tennis rackets reinforced with carbon nanotubes appeared on professional courts, lighter and stronger than their predecessors. Golf clubs, bicycle frames, hockey sticks, all began incorporating nanomaterials. The performance gains were measured in percentages, but at elite levels of competition, those percentages mattered, and the materials trickled down from professional equipment to consumer products. In electronics, nanotechnology was becoming essential. The semiconductor industry had been shrinking transistors for decades, following what was called Moore's Law, the observation that the number of transistors on a chip doubled approximately every 2 years. But as features shrank below 100 nanometers, then 50, then smaller still, the industry crossed fully into the nanoscale realm, and quantum effects that had once been negligible became central challenges to overcome. Engineers learned to work with these quantum phenomena rather than fight them. Gate oxides in transistors thinned to just a few nanometers, so thin that electrons could tunnel through them, a problem that required new materials. Hafnium-based compounds replaced silicon dioxide. Maintaining insulation at atomic scale thicknesses, interconnects between transistors shrank until copper atoms could migrate under the stress of current flow, necessitating barrier layers measured in single-digit nanometers. Each generation of chips required new innovations at the nanoscale. Photolithography, the process of patterning features on silicon wafers, pushed toward ever shorter wavelengths of light, from deep ultraviolet to extreme ultraviolet, light with wavelengths of just 13.5 nanometers to pattern features smaller than the light itself through complex interference effects. The machines that produced these chips became marvels of precision engineering, costing hundreds of millions of dollars each, containing optics polished to atomic smoothness, aligned to tolerances measured in picometers. Meanwhile, in the realm of medicine, nanotechnology opened entirely new approaches to diagnosis and treatment. Researchers developed nanoparticles that could circulate through the bloodstream, seeking out cancer cells. The particles were engineered with exquisite specificity, their surfaces decorated with molecules that recognized markers on tumor cells, antibodies, or peptides that would bind selectively, ignoring healthy tissue. Once attached to cancer cells, these nanoparticles could serve multiple purposes. Some carried chemotherapy drugs, delivering them directly to tumors while sparing healthy tissue from systemic exposure. Others absorbed specific wavelengths of light, infrared or near-infrared, that could penetrate tissue, and when illuminated, they heated up, raising the temperature of the cancer cells they were attached to, cooking them selectively while leaving surrounding tissue unharmed, a technique called photothermal therapy. Still, other nanoparticles were designed for imaging, quantum dots. Nanoscale semiconductors could be tuned to fluoresce in specific colors based on their size, allowing doctors to track multiple biological processes simultaneously, each marked with a different color. Superparamagnetic iron oxide nanoparticles enhanced MRI scans, accumulating in certain tissues and creating contrast that revealed abnormalities invisible in conventional imaging. The challenge with medical nanoparticles was not just reaching the target, but avoiding removal by the body's defenses. The immune system had evolved to clear foreign particles from the bloodstream, and bare nanoparticles would be consumed by macrophages within minutes. Researchers learned to coat particles with polyethylene glycol, a flexible polymer that created a stealth shield, preventing proteins from binding to the surface, allowing the nanoparticles to circulate for hours, long enough to accumulate in tumors through the enhanced permeability that leaky tumor vasculature provided. In energy applications, nanotechnology promised improvements in both generation and storage. Solar cells enhanced with quantum dots could potentially harvest a broader spectrum of sunlight. Perovskite solar cells, materials with nanoscale crystal structures, achieved rapidly improving efficiencies through the 2010s, rising from single digits to over 20% in less than a decade. Though stability remained a challenge, the materials degraded when exposed to moisture, requiring protective encapsulation. Battery technology advanced through nanoscale engineering. Lithium-ion batteries improved as electrode materials were nanostructured, creating more surface area for reactions, allowing faster charging. Silicon, which could theoretically store much more lithium than the graphite conventionally used, had always suffered from expansion during charging, swelling up to 300%, which fractured the material. But silicon nanoparticles or nanowires could accommodate this expansion, bending rather than breaking, enabling new generations of batteries with higher capacity. Catalysis. The acceleration of chemical reactions was revolutionized by nanoscale metals. Gold, which is famously unreactive in bulk form, becomes an excellent catalyst when formed into nanoparticles. The increased surface area and the quantum effects at small sizes combined to make it active for oxidation reactions. Platinum nanoparticles enabled fuel cells, facilitating the conversion of hydrogen and oxygen to water while generating electricity. Every effort was made to maximize the surface area of platinum, to use as little of the expensive metal as possible while maintaining catalytic activity. Environmental applications emerged. Nanoparticles of zero-valent iron could be injected into groundwater to remediate contamination. The particles would react with chlorinated solvents or heavy metals, breaking them down or immobilizing them. Titanium dioxide nanoparticles, when illuminated with ultraviolet light, could break down organic pollutants through photocatalysis, generating reactive oxygen species that oxidized contaminants. This self-cleaning property was incorporated into coatings for buildings and windows, surfaces that could break down dirt and grime when exposed to sunlight. Water filtration benefited from nanoscale membranes, pores sized to exclude bacteria and viruses while allowing water to pass. Carbon nanotube membranes promised exceptional flow rates combined with selective filtering. Graphene oxide membranes could sieve out salt ions, potentially revolutionizing desalination if they could be manufactured at scale. The challenge was always scalability. Moving from laboratory demonstrations to industrial production, from filtering milliliters to filtering millions of liters, textiles incorporated nanoparticles for various effects. Silver nanoparticles provided antimicrobial properties, killing bacteria and preventing odor in athletic outerwear and medical garments. Silica nanoparticles created superhydrophobic surfaces, fabrics that water would beat up and roll off, leaving no trace. Inspired by the lotus leaf effect that nature had perfected, zinc oxide nanoparticles added UV protection to outdoor clothing, blocking harmful radiation while remaining invisible. Food packaging evolved with nanomaterials, barrier films that kept oxygen and moisture out more effectively, extending shelf life. Some packages incorporated nanosensors that could detect spoilage, changing color when food went bad. Nanoparticles of silver were added to cutting boards and food storage containers for antimicrobial effects, though concerns about silver migration into food led to regulatory scrutiny. And here, the story of nanotechnology intersected with questions of safety, of unintended consequences, because materials that behave differently at the nanoscale might also interact with biological systems in unexpected ways. Nanoparticles could potentially cross barriers that larger particles could not. The blood-brain barrier, the cellular membrane, the nuclear envelope. Their small size and high reactivity raised questions about toxicity, about environmental persistence, about how they would move through ecosystems if released. Studies began to examine these questions. Some nanoparticles showed concerning effects. Carbon nanotubes, with their fiber-like shape, raised worries about asbestos-like behavior in lungs. Certain metal oxide nanoparticles generated reactive oxygen species that damaged cells. Others appeared benign, or their effects depended critically on coating, on surface chemistry, on size distribution. The field of nanotoxicology emerged, attempting to understand the rules, to predict which nanomaterials would be safe and which would pose risks. Regulatory frameworks struggled to keep pace. Existing chemical regulations were based on bulk properties, but nanomaterials could have the same chemical composition as bulk materials while behaving entirely differently. Was titanium dioxide at the nanoscale the same substance as bulk, titanium dioxide, for regulatory purposes? Or was it something new that required separate evaluation? Had different jurisdictions answered differently, creating a patchwork of approaches? Public perception of nanotechnology oscillated between enthusiasm and anxiety. Polls showed that most people knew little about the field, but those who did tended toward either optimism about benefits or concern about risks. Science fiction had primed imaginations with scenarios both utopian and dystopian, from medical nanobots that could cure any disease to gray goo scenarios of runaway replication. And while scientists tried to communicate that reality was more nuanced, more incremental, the vivid narratives of fiction often proved more memorable. Through all of this, the work continued in laboratories, in pilot production facilities, in the quiet spaces where fundamental understanding deepened. Researchers mapped the phase diagrams of nanomaterials, determining how properties changed with size, with shape, with surface chemistry. They developed new synthesis methods, learning to control nucleation and growth with increasing precision, to produce uniform particles, to create complex core shell structures, to functionalize surfaces with molecular precision. Characterization techniques multiplied. Transmission electron microscopy revealed internal structures. X-ray diffraction determined crystal phases. Dynamic light scattering measured size distributions. Spectroscopy of various kinds probed electronic and vibrational states, each tool adding a piece to the puzzle of understanding what existed at the nanoscale and how it behaved. The community grew. Journals proliferated. Conferences attracted thousands. Students trained in nanoscience and nanoengineering graduated and joined companies, started ventures, continued research. A whole ecosystem developed. Suppliers of specialized materials and equipment, service providers offering characterization and testing, consultants helping industry navigate the technical and regulatory landscape. And the applications kept expanding, touching more industries, solving more problems, each success building confidence, each challenge revealing complexity. The story was far from over. It was deepening, becoming more intricate, weaving itself into the fabric of technology and society in ways both visible and invisible. As the second decade of the 21st century progressed, nanotechnology began to move beyond its pioneering phase, maturing into something more integrated, more routine, less a revolutionary frontier and more a set of established tools and techniques woven into the fabric of materials science and engineering. The breathless predictions of the early years, the talk of molecular assemblers and nanobots, receded somewhat, replaced by a more measured understanding of what nanotechnology could accomplish and on what timeline. The transformations were real, but they arrived incrementally, through steady refinement rather than sudden breakthrough, through patient optimization of materials and processes rather than science fiction made manifest. In commercial products, nanotechnology became ubiquitous, yet often invisible. Incorporated into formulations and manufacturing processes without fanfare, the average person might use dozens of products containing nanomaterials in a typical day without knowing it. The sunscreen that absorbed UV radiation without leaving white streaks, the stain-resistant fabric of a jacket, the high-efficiency catalyst in a car's exhaust system, the phosphors in an LED screen, the reinforced polymer in a smartphone case. This invisibility was perhaps inevitable. As nanotechnology succeeded, it disappeared into the background, became normalized, no longer something to announce or market explicitly, but simply part of how things were made. The same trajectory followed by countless technologies before it, from synthetic dyes to transistors, from revolutionary novelty to unremarkable infrastructure. The semiconductor industry continued its relentless march towards smaller features. Transistors with gate lengths of 7 nanometers entered production, then 5. The numbers became almost abstract, designations that no longer corresponded literally to physical dimensions but to performance equivalents. A 7 nanometer node might have some features larger than 7 nanometers and others smaller. The nomenclature had become a marketing metric as much as a technical one. At these scales, every aspect of a chip manufacturing operated in the nanoscale realm. The lithography masks were nanoscale artifacts, the etch processes controlled with atomic precision, the deposition of thin films measured in monolayers. Entire chips could contain billions of transistors, each one a nanoscale device, all operating in concert, processing information at speeds that would have seemed impossible just decades earlier. Yet even here, limits were appearing, not the fundamental limits that physics might impose, but practical limits of cost and complexity. Each new generation of manufacturing equipment became exponentially more expensive. The extreme ultraviolet lithography machines required to pattern the smallest features cost hundreds of millions of dollars each. Operated by companies that could be counted on one hand, the barrier to entry had become insurmountable for all but the largest corporations and most advanced economies. And so the industry began to shift, looking not just at making things smaller, but at new architectures, three-dimensional stacking of chips, new materials like gallium nitride or silicon carbide for power electronics, photonic interconnects using light instead of electrons, quantum dots for displays, each innovation drawing on nanoscale understanding but applying it in new configurations. In medicine, the early promise of targeted drug delivery began to bear fruit in approved therapies. Liposomal formulations of chemotherapy drugs reached the market, nanoparticles of albumin carrying paclitaxel, nanoscale iron oxide for treating anemia. These were not the molecular machines of speculative fiction, but they were proof that nanoscale engineering could improve treatment, could reduce side effects, could make existing drugs more effective. Cancer treatment in particular became a focus because tumors had properties that nanomedicine could exploit. Their leaky vasculature allowed nanoparticles to accumulate preferentially, a phenomenon called the enhanced permeability and retention effect. Particles between 10 and 100 nanometers could extravasate from tumor blood vessels and remain trapped in the tumor microenvironment, while being too large to escape normal vasculature. This passive targeting provided a baseline improvement, and when combined with active targeting through surface molecules that recognized tumor markers, the cell activity improved further, clinical trials multiplied, testing nanoparticles for diagnostics and therapy. Some succeeded, many did not. The translation from animal models to humans proved challenging. What worked in mice did not always work in people. The immune system's response to nanoparticles was more complex than initially appreciated. The protein corona, a layer of proteins that adsorbed to nanoparticle surfaces within seconds of entering the bloodstream, could alter targeting and clearance in unpredictable ways. Researchers learned humility, recognized that biology was more intricate than the models had suggested, that each type of nanoparticle, each coating, each surface chemistry would behave slightly differently, that personalized medicine might require personalized nanoparticles tuned to an individual patient's biology, a challenge of complexity that would take years to unravel. In energy storage, the improvements from nanomaterials accumulated. Lithium-ion batteries in electric vehicles benefited from nanostructured electrodes. Silicon nanowires or nanoparticles mixed with graphite, allowing for higher energy density without the catastrophic failure that bulk silicon experienced. Separator membranes with nanoscale pores improve safety by preventing dendrite formation, the growth of lithium fingers that could short-circuit cells and cause fires, supercapacitors, devices that stored energy through charge separation rather than chemical reactions, advanced through nanomaterials with enormous surface area, graphene, activated carbon, metal oxides, materials where nearly every atom was at the surface, accessible for charge storage. These devices could charge and discharge much faster than batteries, thousands of cycles without degradation, but stored less total energy. They found applications where rapid power delivery mattered, in regenerative braking systems, in grid stabilization, in complementing batteries rather than replacing them. Solar energy conversion explored new frontiers at the nanoscale. Quantum dots could theoretically harvest hot electrons before they lost energy as heat, potentially exceeding the Shockley-Queisser limit that capped the efficiency of conventional solar cells. Perovskite solar cells, with their nanoscale crystal structure and unusual electronic properties, achieved efficiencies rivaling silicon while potentially offering cheaper manufacturing. But stability remained the persistent challenge. The materials degraded with exposure to moisture, to oxygen, to heat, to light itself. Encapsulation helped, but added cost and complexity. Photocatalytic water splitting, using sunlight to generate hydrogen fuel from water, became an area of intense research. Titanium dioxide and other metal oxides could split water when illuminated, but inefficiently, requiring UV light and suffering from rapid recombination of the generated charges. Nanostructuring helped, creating junctions and surface states that improved charge separation. Doping with other elements shifted the absorption into the visible spectrum. Yet the efficiency remained too low for practical hydrogen production. The goal tantalized, but stayed just out of reach. Environmental remediation continued to find applications for nanomaterials, though not always as originally envisioned. Nanoparticulate zero-valent iron could indeed clean contaminated groundwater, but it tended to aggregate, to lose reactivity, to be immobilized by the soil matrix. Success required careful site characterization and often repeated injections. Photocatalytic titanium dioxide could break down pollutants but needed UV light and worked slowly. Real-world conditions were messier than laboratory demonstrations, yet in specific contexts, for specific contaminants, the approaches proved viable. Air filtration advanced through nanofiber materials, electrospun polymers creating webs with fiber diameters in the hundreds of nanometers. These filters could capture particles with high efficiency while maintaining low pressure drop, allowing air to flow through easily. They appeared in respirators, in HVAC systems, in cleanroom applications, a practical implementation of nanoscale structure for macroscale benefit. The conversation around safety evolved. Early fears of wholesale catastrophe faded, replaced by more nuanced concern about specific materials in specific contexts. Carbon nanotubes in aerosolized form raised legitimate questions about pulmonary exposure, but embedded in composites they posed minimal risk. Silver nanoparticles released from textiles into waterways could affect aquatic organisms, but the concentrations and ecological impacts required careful study. Zinc oxide and titanium dioxide in sunscreens were extensively tested and generally found safe, though concerns lingered about environmental accumulation. Regulatory approaches varied by region. Europe adopted a precautionary stance, requiring nanomaterials to be specifically assessed, even if the bulk form was approved. Labeling requirements appeared for cosmetics and food containing nanomaterials. The United States took a more case-by-case approach. Existing regulations for chemicals were applied, but with guidance acknowledging nanoscale specificity. Industry developed voluntary reporting schemes, sharing information about nanomaterial use and safety testing. The toxicology research deepened in sophistication, moving beyond simple cell viability assays to mechanism-based understanding. How did nanoparticles interact with proteins, with cell membranes, with organelles? What determined whether they would be toxic or benign? Shape mattered, surface charge mattered, coating mattered. Even the synthesis method could leave residues that affected biological response. The field learned to control these variables, to design for safety as well as function. Public engagement efforts attempted to demystify nanotechnology. Science museums created exhibits. Educational programs brought nanoscience into classrooms. Researchers participated in dialogue with communities and stakeholders. The goal was informed discussion rather than either uncritical enthusiasm or reflexive fear, though achieving that balance proved difficult. The technical complexity made simple explanations challenging, and the absence of dramatic incidents meant public attention remained limited. Investment patterns shifted. The initial wave of venture capital that had flowed into nanotechnology startups in the early 2000s began to ebb as returns proved slower than anticipated. Some companies succeeded, creating viable businesses in specialty materials, in coatings, in composites. Others pivoted or folded. The timeline for commercialization stretched longer than optimistic projections had suggested, but patient capital and strategic partnerships kept development moving forward. Academic research diversified, moving beyond the initial gold rush mentality where every department wanted a nanotechnology center, toward more focused investigations of specific questions. How to control chirality in carbon nanotubes to separate metallic from semiconducting types. How to scale up production of graphene while maintaining quality. How to stabilize perovskites for long-term operation. How to deliver RNA therapeutics using lipid nanoparticles. Each question narrow but important, each contributing to the larger edifice of understanding. Interdisciplinary collaboration became not just encouraged, but essential. No single discipline could address the complexity of nanoscale systems. Physicists brought understanding of quantum mechanics and solid-state phenomena. Chemists contributed synthesis expertise and surface chemistry knowledge. Biologists understood cellular interactions and immune responses. Engineers translated insights into manufacturable processes and scalable designs. The boundaries between fields blurred. Researchers became fluent in multiple languages, comfortable moving between quantum mechanics and cell biology, between molecular dynamics, simulations, and clinical trials. And as the field matured, as the initial excitement settled into sustained effort, a different kind of appreciation emerged, not for revolutionary transformation arriving suddenly, but for the quiet power of incremental improvement, the accumulated benefit of countless small advances, materials a bit stronger, processes a bit more efficient, devices a bit more capable, each change modest, but compounding over time into substantial progress. The story of nanotechnology was revealing itself to be not a single dramatic breakthrough, but a gradual weaving of capability, a patient accumulation of knowledge and technique, a deepening relationship between human intention and atomic reality. And in this slower, steadier unfolding, there was perhaps something more profound than the flash of revolution, something that spoke to the nature of understanding itself, to the way insight is built, layer upon layer, atom upon atom, until the invisible becomes visible, and the impossible becomes routine. The work continued in laboratories that hummed with controlled precision, in manufacturing facilities where nanomaterials were produced by the ton, in hospitals where nanoparticles drugs circulated through patients' veins. In the silicon chips processing these very words, nanotechnology had become infrastructure, had become the substrate on which other advances were built. And in that transformation from frontier to foundation, it had succeeded in ways both quieter and more lasting than the early visions had imagined. To understand nanotechnology at its most profound level is to understand something about the nature of reality itself, about the way matter organizes, the way complexity emerges from simplicity, the way the universe builds elaborate structures from elementary components. At the nanoscale, the distinction between living and non-living begins to blur. A virus, after all, is a nanoscale object, neither fully alive nor entirely inert, a protein shell containing genetic instructions, somewhere between chemistry and biology. And when scientists build nanoparticles that carry genetic material into cells, that recognize molecular signatures and respond, that self-assemble and perform functions, they are creating objects that occupy the same ambiguous territory, molecular machines that echo life's strategies without being alive. The cell itself is the master nanotechnologist. Every moment, in every living organism, molecular machines are at work. Ribosomes translate genetic code into proteins, adding amino acids one at a time with atomic precision. Motor proteins walk along cytoskeletal tracks, carrying cargo through the cellular interior, each step powered by the hydrolysis of ATP, each movement the result of conformational changes measured in nanometers, ion channels open and close, creating electrical signals through selective passage of atoms, sodium, potassium, calcium, each recognized and transported with exquisite specificity. When human-designed nanotechnology works, it does so by learning from these biological examples, by mimicking the strategies that evolution discovered, self-assembly, where components find each other and organize spontaneously, driven by thermodynamics, by the tendency of systems to minimize free energy. DNA, origami, folds nucleic acids into precise shapes through Watson-Crick base pairing, each adenine finding its thymine, each guanine finding its cytosine, creating scaffolds and structures with nanometer resolution, not through external manipulation but through internal instruction, information encoded in sequence becoming manifest in form. Proteins fold through similar principles, a chain of amino acids collapsing into a unique three-dimensional structure, guided by hydrophobic and hydrophilic interactions, by hydrogen bonds and disulfide bridges, by the fundamental forces that operate at the nanoscale. And when that folding goes wrong, when proteins misfold and aggregate, diseases like Alzheimer's and Parkinson's result. Plaques and tangles at the nanoscale, creating dysfunction at the scale of organs and organisms. Another reminder that size does not determine significance. There is something almost meditative in contemplating these processes, the constant molecular dance, the thermal fluctuations that keep everything in motion, the Brownian jitter, that at the nanoscale is not a disturbance, but a fundamental aspect of existence. Particles diffusing through solution, not by swimming, but by being jostled, buffeted by collisions with water molecules, millions of impacts per second, creating a random walk that nevertheless leads to mixing, to equilibration, to the spread of molecules through space. Nanotechnology harnesses these fluctuations, uses randomness productively. Nanoparticles find their targets not through directed movement but through diffusion and recognition. Billions of particles released into the bloodstream, each one wandering, each collision a chance for recognition, for binding, and the specificity comes not from guidance but from the shape of molecules, from the lock and key fit of receptor and ligand, from the same principles that govern enzyme-substrate interactions and antibody-antigen recognition. The colors of nanomaterials arise from a quantum confinement, from the fact that electrons trapped in spaces comparable to their wavelength behave differently, their energy levels discretize, and the gaps between those levels determine which photons they absorb and emit. Quantum dots glow in colors tuned by their size. Smaller dots emit blue light, larger ones red, because the confinement is stronger or weaker, the same material, the same composition, but different colors purely from geometry, from the prison of dimension. Gold nanoparticles display their reds and purples through plasmon resonance, collective oscillations of surface electrons. Driven by the electromagnetic field of light, the frequency of oscillation depends on size and shape. On the dielectric environment, spheres resonate at different wavelengths than rods. Particles close together couple their plasmons, shifting the resonance again. This is how ancient artisans created the Lycurgus cup, a Roman glass that appears jade green in reflected light but ruby red when illuminated from within. Gold nanoparticles suspended in glass, creating color through nanoscale structures centuries before anyone understood the mechanism. The strength of materials at the nanoscale often approaches theoretical limits because defects, the dislocations and grain boundaries that allow materials to deform, become less probable in smaller volumes. A carbon nanotube is essentially a perfect crystal, every atom bonded correctly, and so its strength reflects the strength of a carbon-carbon bonds themselves, not weakened by flaws. This is why materials that are brittle in bulk can be flexible at the nanoscale, why whiskers and nanowires can bend and recover, sustaining strains that would shatter larger structures. Surface energy dominates at small sizes, because the ratio of surface atoms to interior atoms grows. A nanoparticle of 10 nanometers diameter might have half its atoms at the surface, each one experiencing incomplete bonding, dangling bonds reaching into empty space. This creates reactivity, a driving force for aggregation, for coating, for interaction with the environment. It is why nanoparticles must be stabilized, protected, given shells or surface layers that satisfy those dangling bonds and prevent unwanted reactions. Heat flows differently. Electrons behave quantum mechanically, tunneling through barriers, existing in superpositions, entangling across distances. The nanoscale is where the classical world transitions to the quantum, where everyday intuition fails and stranger rules apply. And learning to work in this regime requires not just new techniques, but new ways of thinking. Comfort with probability rather than certainty, with wave-particle duality, with the observer effect where measurement itself changes what is measured. There is humility in this, recognition that control at the nanoscale is always partial, always negotiated with the laws of physics, always a conversation between intention and possibility. Researchers propose, nature disposes, and the wisdom lies in learning to listen, to understand what the system wants to do, what configurations are favorable, what processes will proceed spontaneously, and then aligning human goals with those natural tendencies rather than fighting against them. And so the story of nanotechnology returns to where it began, to the invisible realm that underlies all visible things, to the atomic foundations of matter and the molecular machinery of life, to the space where human ingenuity meets fundamental law and creates something new from ancient elements. The work continues, though perhaps now with different expectations, with patience for the long development cycles that real innovation requires, with acceptance that transformation comes through accumulation rather than revolution, that each small advance in understanding, each improved synthesis, each optimized formulation contributes to a larger progression that may only become clear in retrospect. In laboratories around the world, at this very moment, researchers are positioning atoms, synthesizing molecules, characterizing structures, testing materials, each one adding their thread to a tapestry whose full pattern remains incomplete, whose ultimate form cannot yet be known. Because nanotechnology is not a fixed destination, but an ongoing exploration, a continuous deepening of the relationship between human capacity and natural possibility. The technologies that emerge from this work blend into daily life, becoming transparent through familiarity. The smartphone in a pocket contains more nanotechnology than could have been imagined just decades ago. From the nanoscale transistors in its processor to the quantum dots in its display, from the lithium-ion battery with its nanostructured electrodes to the sensors that detect motion and orientation through nanoscale mechanical elements, all of it invisible, all of it essential. In hospitals, nanoparticles circulate through patients' blood, seeking tumors, delivering drugs, improving outcomes in ways both measurable and meaningful. The revolution is quiet, incremental, but no less real for its subtlety. Each life extended, each side effect reduced, each diagnosis made earlier, accumulating into substantial benefit. The environmental applications proceed. Nanofiltration membranes purifying water, photocatalytic surfaces breaking down pollutants. Though the grand visions of planetary remediation have given way to more modest but achievable goals, targeted interventions, specific solutions to specific problems, progress measured in increments rather than transformations, and the fundamental research deepens because there is always more to understand, more phenomena to explore at the boundary between classical and quantum, between order and chaos, between the designed and the emergent, each answer revealing new questions, each solved problem exposing further complexity. The work is inexhaustible because nature's creativity at the nanoscale appears unlimited. Perhaps this is the ultimate lesson of nanotechnology, that smallness contains multitudes, that the invisible world is as rich and intricate as any cosmos, that there is no scale at which reality becomes simple, only scales at which different principles dominate, different symmetries emerge, different possibilities open. The story does not end, it only pauses, like a conversation interrupted but not concluded, like a question asked but not fully answered. Because nanotechnology is still unfolding, still revealing itself, still teaching those who work with it about the nature of matter, about the art of precision, about what becomes possible when human intention engages with atomic reality. In the quiet of clean rooms, in the hum of instruments measuring the unmeasurable, in the glow of monitors displaying structures too small for any eye to see, the work continues, patient, methodical, incremental, building the future atom by atom, molecule by molecule, one careful placement at a time. And there is beauty in this, in the dedication to understanding, in the persistence required to work at scales where every environmental vibration matters, where contamination arrives unseen, where success demands not just knowledge but craft, not just theory but touch, the ability to sense through instruments, to feel through data, to know when the system is behaving as it should. The nanoscale world persists in its dance, atoms oscillating, electrons tunneling, molecules diffusing, all the ceaseless motion of matter at its most fundamental level, indifferent to human observation, following rules that existed long before consciousness arose to study them, rules that will continue long after, eternal, patient, waiting to be understood a little more deeply, used a little more wisely, appreciated a little more fully, and in that appreciation, in that wonder at the complexity hidden in simplicity, at the order emerging from chaos, at the way structure at the smallest scales creates properties at larger ones, there is a kind of peace, the peace of understanding, and however partial, however incomplete, that the universe makes sense, that there are patterns to discover, principles to learn, beauty to witness, even in the realm of the infinitesimal. The story fades, as all stories must, but the reality it describes continues invisible, essential, the nanoscale foundation on which everything else is built, atoms and molecules, assembling, interacting, creating, the endless dance of matter at the edge of perception, at the heart of everything. The sky is a canvas, and it changes every moment, without permission, without warning, just movement and light, and the slow exhale of the atmosphere above us. Tonight, the air feels different. There is weight to it, a thickness that suggests something is gathering, something immense and patient. And if we pay attention, if we allow ourselves to notice, we can sense the invisible architecture of the world's breath, the way pressure builds and releases, the way moisture climbs and falls, the way temperature shapes everything it touches. This is the realm of clouds and currents, of frontings that slide across continents like thoughts across a mind, of systems that spiral and pulse with a logic all their own. And to understand this realm is to understand that the air around us is never still, never empty, never merely background to our lives. It is always moving, always transforming, always carrying stories written in vapor and temperature and the subtle mathematics of evaporation. I have come to think of the atmosphere as a kind of living text, one that requires no translation, only attention, only the willingness to look up and recognize that what we call weather is not chaos, but pattern, not randomness, but the intricate unfolding of laws so fundamental they govern oceans and breath alike. There is a particular quality to the light just before a change in weather, a softening or sometimes a sharpening of the edges of things. And those who spend their lives watching the sky learn to read these shifts the way others might read a clock or a face or the surface of water disturbed by something moving beneath. The science of this watching, this patient observation of what the heavens do, has a name that sounds almost like poetry itself. Meteorology, from the Greek word meteoron, meaning things in the air, things aloft. And for thousands of years, humans have looked upward and wondered at and built systems of understanding from that wondering. Tonight, as the air presses close and the sky holds its particular shade of gray-blue, I find myself tracing the history of that wondering, the long, slow accumulation of knowledge about wind and rain, about the invisible rivers of air that flow above us, about the delicate instruments we have built to measure what cannot be seen but only felt. Because the atmosphere does not reveal itself easily, it requires instruments, imagination, and a kind of patience that measures itself not in minutes but in seasons, in years, in the careful comparison of one winter to another, one hurricane season to the next. And yet, for all our instruments and satellites and computer models, there remains something fundamentally mysterious about the sky, something that resists complete knowing, and perhaps that is part of what draws us to study it, the way it remains always slightly beyond our grasp, always capable of surprise. The temperature is dropping now, just slightly, a change so subtle it registers more as a feeling than a fact. And this feeling is itself a kind of data, the body's own meteorological station, reading the air through skin and breath, through the slight quickening of pulse that comes when pressure falls. Ancient peoples knew this feeling well. They watched birds and the behavior of smoke, the direction of clouds at sunrise, the smell of rain carried on wind from distant mountains. And from these observations, they built the first forecasts, the first attempts to say what the sky might do tomorrow, next week. When the planting season came, it was not always science in the way we understand science now. It was closer to art, or to the kind of knowledge that comes from living in intimate relationship with a place, knowing its moods, its tendencies, its rhythms across the wheel of the year. But even then, even in that pre-scientific watching, there was accuracy, there was real understanding, because the atmosphere is not arbitrary. It follows laws, and those laws can be learned through attention, through the careful noting of what precedes what follows what what patterns repeat and which do not. And so the story of meteorology is not just the story of instruments and equations, though those will come. It is first the story of noticing, of the human impulse to make sense of the forces that surround us, to find order in the shifting vault of sky. The wind is picking up slightly, moving through invisible corridors, following paths determined by the rotation of the earth, by the heating of land and sea, by 1,000 factors that interweave to create this particular breeze at this particular moment, and nowhere else, and never quite this way again. The first person to truly think about the sky as something that could be understood rather than merely feared or revered may have been a Greek philosopher standing on a hillside sometime in the 4th century before the Common Era, watching clouds build over the Aegean Sea. His name was Aristotle, and in approximately 340 BCE, he wrote a text he called Meteorologica, a word that would eventually give us our modern term for the study of weather. Though his book covered far more than what we now think of as meteorology, it included thoughts on comets and earthquakes, on rainbows and thunder, on everything that happened in the realm between the earth and the moon. Aristotle believed that weather arose from exhalations, vapors that rose from the earth and interacted with heat and cold in the upper air. And while this theory would eventually prove incomplete, there was something profound in his basic intuition, that weather was not divine caprice, but natural process, something that could be observed and reasoned about. He noticed that rain came from clouds, that clouds formed when moist air cooled, that wind had patterns and directions that varied with the seasons, and he tried to organize these observations into a coherent system, a way of thinking about the atmosphere that made sense of its endless variations. For nearly 2,000 years, his text remained the foundational work on weather, copied and studied and argued over, even as other aspects of natural philosophy evolved. Meteorology remained largely where Aristotle had left it, a collection of observations and theories, but no systematic method of measurement, no instruments to make the invisible visible. The sky kept its secrets because there was no way to weigh the air, no way to measure its pressure or humidity with precision, no thermometer to say exactly how cold the rain was or how warm the summer wind. But slowly, over centuries, the tools began to emerge. In the early 1600s, a man named Galileo Galilei created a device called a thermoscope, a glass tube with a bulb at one end, open at the other, placed upside down in a basin of water, and as the air in the bulb warmed or cooled, the water level in the tube would fall or rise, not perfectly, not with precise numbers, but visibly, measurably. And this was the beginning of something new. The air had temperature, and temperature could be seen. A few decades later, in 1643, Galileo's student Evangelista Torricelli made an even more remarkable discovery. He filled a glass tube with mercury, sealed at one end, and inverted it into a dish of mercury, and the column of mercury in the tube fell, but not all the way. It stopped at a certain height, held there by something invisible, the weight of the air, pressing down on the mercury in the dish, holding the column aloft. This was the barometer, the first instrument to measure atmospheric pressure, and with it came a revelation. The air had weight, substance. It pressed down upon us with measurable force, and that force changed, rising and falling in ways that seemed connected to changes in weather. Torricelli noticed that before storms, the mercury column would fall, the air pressure dropping as the weather system approached, and before clear weather, the column would rise. And this meant that the atmosphere was not uniform, not constant, but dynamic, full of invisible waves and gradients that might be predictable. The same era brought the invention of the hygrometer, a device to measure moisture in the air, first attempted by Nicholas of Cusa in the 1400s using wool, which grew heavier as it absorbed moisture from humid air, and later refined by others using hair, which lengthens and shortens with changes in humidity. A phenomenon you can observe even now if you watch someone's hair react to a foggy morning. These instruments, simple as they were, transformed meteorology from philosophy to science, because now observers could attach numbers to their observations, could compare conditions in different places, could track changes over time with precision, and people began to keep weather journals, daily records of temperature and pressure and wind direction, small acts of documentation that accumulated into something larger, a growing archive of data, the atmosphere's autobiography written one day at a time. In England, a scientist named Robert Hooke proposed in 1663 that a network of observers should be established, all using standardized instruments, all recording their observations at the same times each day, so that weather patterns across a region could be understood, so that the movements of storms and fronts could be tracked. It was a vision ahead of its time, because the infrastructure did not yet exist. The instruments were not yet standardized. The means of communicating observations across distances was too slow. But the idea was planted that meteorology required coordination, collaboration, a shared project of watching the sky together. Meanwhile, in France, René Descartes was thinking about clouds, about how they formed and why they appeared in certain shapes. He proposed that tiny particles of water in the air came together to form visible vapor, an idea that moved closer to our modern understanding, though he lacked the ability to verify it in detail. And in 1667, Robert Hooke conducted an experiment that would prove foundational. He showed that air was necessary for combustion, and in doing so, began to reveal that the atmosphere was not a simple substance, but a mixture, composed of different elements with different properties. This would eventually lead to the discovery that air was primarily nitrogen and oxygen, with small amounts of other gases, each playing a role in the complex chemistry of weather, though that understanding would take more than another century to fully develop. The 1800s brought new energy to meteorology, driven by two forces, the spread of the telegraph and the increasing toll of storms on commerce and human life. Ships were lost at sea during hurricanes that struck without warning. Cities were battered by storms that seemed to arrive from nowhere. And as industrial society grew more complex, more dependent on transportation and trade, the cost of weather ignorance grew higher. In 1849, the Smithsonian Institution in the United States began organizing a network of volunteer weather observers, eventually numbering more than 600 stations, all telegraphing their observations to Washington each day, where they could be compiled into maps showing weather conditions across the continent. For the first time, meteorologists could see weather as a spatial phenomenon, not just what was happening here, but what was happening there, and over there, and how those conditions related to one another, the maps revealed something extraordinary. Storms moved. They traveled across the landscape like invisible entities, following paths that could be traced, and if they could be traced, perhaps they could be predicted. A French scientist named Urbain Le Verrier became convinced of this possibility after a devastating storm struck the Black Sea in 1854, sinking Allied ships during the Crimean War. Le Verrier collected weather observations from across Europe on the day of the storm and the days before, and he showed that the storm had formed far to the west, had moved eastward in a trackable progression, and that if telegraphic warnings had existed, the ships could have been saved. This demonstration led to the establishment of storm warning services in France and then across Europe. The first organized attempts at weather forecasting, simple warnings based on observed conditions, telegraphed ahead of approaching storms. And in 1870, the United States established its own weather service, initially run by the Army Signal Corps, with observers stationed across the country, sending coded telegrams about temperature, pressure, wind, precipitation, and cloudiness 3 times each day. The data flowed to central offices where meteorologists drew maps, analyzed patterns, and issued forecasts, cautious predictions about what the weather might do in the next 12 to 24 hours. These early forecasts were crude by modern standards, often wrong, sometimes spectacularly so, but they represented a fundamental shift in humanity's relationship with the sky, from passive observation to active prediction, from acceptance to anticipation. The theoretical understanding was advancing too. In the late 1800s, a Norwegian scientist named Wilhelm Bjerknes proposed that weather forecasting could become an exact science if enough observations could be gathered and enough mathematical calculations performed. The future state of the atmosphere could be computed from its present state. Weather as a problem in physics and mathematics. It was a beautiful idea, but practically impossible with the technology of the time. The calculations required were so numerous and complex that a human working with pencil and paper could not complete them faster than the weather actually changed. But the idea persisted and would wait for machines that could think faster than humans, machines that did not yet exist, but would come in time, as all tools eventually come when they are needed enough. The early decades of the 20th century brought meteorology into a new phase, one defined by war and necessity, because weather suddenly mattered in ways it never had before. Aircraft were taking to the skies, fragile machines of wood and fabric that could be torn apart by wind shear or brought down by icing, and pilots needed to know what waited for them in the clouds, what conditions lay ahead, whether the ceiling was high enough to navigate by sight or whether fog would trap them blind above unfamiliar terrain. The First World War made this urgency absolute. Battles were planned around weather. Artillery trajectories were calculated with wind speed and direction. Poison gas attacks depended on favorable winds, and aircraft reconnaissance missions required clear skies or at least predictable cloud cover. And so meteorology became a military science taught to officers, integrated into operations, given resources and attention it had never received in peacetime. It was during this period, in the midst of that great conflict, that a Norwegian physicist named Wilhelm Bjerknes and his colleagues developed what would become known as the Bergen School of Meteorology, a revolutionary new way of understanding storms and weather systems. They were working in neutral Norway, relatively isolated from the war, but deeply affected by it nonetheless. Food was scarce, shipping was disrupted, and accurate weather forecasts became essential for the small fishing fleet that kept the population fed. Björknes and his team, which included his son Jakob and a brilliant young meteorologist named Tor Bergeron, began analyzing weather data with fresh eyes, looking for patterns that earlier meteorologists had missed, and they found something remarkable. They discovered that the atmosphere was not a gradual continuum of temperature and pressure, but rather divided into distinct masses of air, each with its own characteristics, its own temperature and humidity and density. A mass of cold air moving down from the Arctic, a mass of warm, moist air flowing up from the tropics. And where these masses met, something dramatic happened. The boundary between them was not smooth, not gradual, but sharp, a front like the front line of a battle, where two opposing forces collided, and along these fronts weather happened. Clouds formed, precipitation fell, winds intensified, because the different air masses did not blend peacefully. They fought, the cold air pushing under the warm air like a wedge, forcing it upward, and as the warm air rose, it cooled, and its moisture condensed, and rain or snow or thunderstorms erupted along the boundary. This was the polar front theory, and it explained so much that had been mysterious: why storms formed where they did, why they moved the way they moved, why certain cloud patterns preceded certain weather changes. The Bergen School introduced an entire vocabulary that meteorologists still use today: cold fronts and warm fronts, occluded fronts where a faster-moving cold front overtakes a warm front, stationary fronts where neither air mass advances, and the cyclones that form along these boundaries. Vast rotating systems hundreds or thousands of miles across, spinning counterclockwise in the northern hemisphere due to the Coriolis effect, that subtle force created by Earth's rotation. They drew weather maps that showed these fronts as lines with symbols: triangles for cold fronts, semicircles for warm fronts, a notation system that made the invisible structure of the atmosphere suddenly visible, suddenly comprehensible. And forecasters who learned to read these maps, who understood the life cycle of a mid-latitude cyclone, could predict with much greater accuracy what the weather would do in the coming hours and days. A warm front approaching meant steady rain or snow, clouds thickening from high cirrus to altostratus to nimbostratus, temperatures rising, winds shifting from east to south. A cold front meant a narrow band of intense weather, possibly thunderstorms, followed by clearing skies, dropping temperatures, winds veering from south to west to northwest. These patterns repeated endlessly across the middle latitudes where warm and cold air masses perpetually contested, where the atmosphere never found equilibrium but remained in constant dynamic tension. Meanwhile, other mysteries of the atmosphere were being unraveled. In the early 1930s, a pilot and meteorologist named Carl Gustav Rossby began studying the large-scale circulation patterns of the upper atmosphere, the rivers of air that flowed above the weather we experience at ground level. He discovered that the upper atmosphere contained waves, vast undulations in the jet stream, the narrow band of extremely fast winds that circles the globe at altitudes of 30,000 to 40,000 feet. These waves, which came to be called Rossby waves, meander north and south as they flow west to east, and their position and amplitude control where storms develop, where cold air plunges southward, where warm air surges northward. A deep trough in the jet stream creates conditions for storm development, while a ridge brings fair weather, and the waves themselves move and evolve, creating a dynamic pattern that influences weather across entire continents. Understanding the jet stream transformed meteorology because weather at the surface is ultimately driven by conditions aloft, by the circulation patterns at 5 miles up, where temperature differences between equator and poles create winds so powerful they can carry an aircraft backward despite its engines running at full thrust. The 1940s brought another revolution, radar. Developed during the Second World War to detect aircraft, radar could also detect precipitation, the radio waves bouncing off raindrops and ice crystals, returning echoes that could be displayed on a screen. And suddenly meteorologists could see inside storms, could watch squall lines march across the countryside, could identify the spiral bands of hurricanes, could spot the hook echo signature of a tornado-producing thunderstorm. Weather was becoming visible in new ways. Not just the clouds we could see with our eyes, but the three-dimensional structure of precipitation, the intensity gradients within a storm, the movement and evolution of systems too large or too fast or too hidden by darkness to observe directly. The same decade brought another tool, the radiosonde, a small package of instruments carried aloft by weather balloon, measuring temperature and humidity and pressure as it rose, transmitting the data back to ground stations via radio twice a day at coordinated times around the world. Weather balloons were launched, rising through the troposphere, the layer of atmosphere where weather happens, up into the stratosphere beyond, sending back a vertical profile of atmospheric conditions. These soundings revealed the three-dimensional structure of the atmosphere, showing meteorologists not just what was happening at ground level, but how temperature and moisture and wind varied with altitude. Information essential for understanding storm development, for predicting whether scattered clouds would grow into thunderstorms, for knowing how stable or unstable the air mass was, and the data from thousands of these balloon launches collected over decades built up a climatology, a baseline understanding of what the atmosphere typically looked like at different times and places, against which unusual conditions could be identified. The 1950s brought the beginning of the computer age, and with it, the possibility that Wilhelm Bjerknes's dream of mathematical weather prediction might finally become practical. A mathematician named John von Neumann became fascinated by the challenge, and in 1950, a team he assembled made the first numerical weather prediction using ENIAC, one of the first electronic computers, to calculate how a simplified model of the atmosphere would evolve over 24 hours. The calculation took 24 hours to complete, which meant it was useless for actual forecasting, but it proved the concept weather could be computed. The equations of fluid dynamics and thermodynamics that governed atmospheric behavior could be solved numerically, and the results resembled actual weather patterns. As computers grew faster, and as the equations became more sophisticated, and as more observational data became available to initialize the models, numerical weather prediction became practical, then standard, then indispensable, By the 1960s, computers were running forecast models twice daily, calculating the expected evolution of weather patterns days into the future. And forecasters used these guidance products alongside their own experience and judgment to make predictions. And the forecasts were getting better, measurably better. Forecast accuracy was improving year by year as models improved and data coverage expanded. The 1960s also brought weather satellites. First TIROS-1 in 1960, sending back grainy black and white images of clouds. And for the first time, humans could see the weather systems they had been mapping from ground observations, could see the spiral structure of the mid-latitude cyclones, the clear eye of hurricanes, the vast blankets of stratus covering ocean basins. Satellites revealed the global atmosphere as a connected system, showed weather patterns over oceans and remote regions where no observers existed, provided continuous monitoring of developing storms and moving fronts. Later, satellites carried instruments beyond simple cameras, infrared sensors that could measure cloud top temperatures, microwave sensors that could see through clouds to measure precipitation, instruments that could profile atmospheric temperature and moisture from space, and the data flowed down to forecasting centers, was ingested into computer models, improved the initial conditions from which forecasts were calculated, and accuracy continued to improve. The late 20th century brought a deepening understanding of the atmosphere's complexity, an awareness that weather was not isolated phenomenon, but part of larger patterns, rhythms that pulsed across seasons and years and decades. Meteorologists began to recognize teleconnections, relationships between weather patterns in distant parts of the globe, the way conditions in the tropical Pacific could influence winter storms over North America, or how sea surface temperatures in the Indian Ocean could affect monsoons in Asia and droughts in Australia. The most famous of these patterns became known as El Niño, a warming of the eastern tropical Pacific that occurred every few years, disrupting normal weather patterns worldwide. Fishermen off the coast of Peru had known about it for centuries, noticing that some years the cold, nutrient-rich waters they depended on would give way to warm, sterile currents, and the anchovy fishery would collapse. And this often happened around Christmas, so they called it El Niño, the boy child, in reference to the Christ child. But meteorologists in the 1960s and 70s discovered that El Niño was not just a local phenomenon. It was coupled with changes in atmospheric pressure across the entire tropical Pacific, a seesaw of pressure between Indonesia and Tahiti that controlled trade winds and ocean currents and rainfall patterns. This coupled ocean atmosphere system, which scientists named the El Niño Southern Oscillation, or ENSO, influenced weather globally during El Niño years. Certain regions tended toward drought, while others received unusual rainfall. Winter storms tracked differently across North America. Hurricane activity shifted in the Atlantic. Understanding ENSO gave meteorologists a window into seasonal forecasting, the ability to say with some confidence that the coming winter might be wetter or drier, warmer or cooler than average, not day by day, but in general tendency. Other oscillations were discovered too. The North Atlantic Oscillation, the Pacific Decadal Oscillation, the Madden-Julian Oscillation, each operating on different timescales, each influencing weather in different ways, and all interacting with one another in a vast symphony of atmospheric motion. The atmosphere was revealing itself as far more interconnected than anyone had imagined, a single fluid system wrapping the entire planet, where disturbances in one region propagated in waves and eddies to distant continents, where everything influenced everything else. And as this understanding grew, another realization emerged, that human activity was beginning to change the composition of the atmosphere itself. The concentration of carbon dioxide in the air, produced by burning fossil fuels, was rising measurably, and carbon dioxide trapped heat, absorbing outgoing infrared radiation and re-radiating it back toward the surface. Scientists had understood this greenhouse effect since the 19th century. A Swedish chemist named Svante Arrhenius had calculated as early as 1896 that doubling atmospheric carbon dioxide would warm the planet, but it had seemed a distant theoretical concern, something that might matter in centuries to come. By the late 20th century, it was becoming clear that the change was happening faster than anticipated, and that it would profoundly affect weather and climate, the two terms often confused but meteorologically distinct. Weather is the specific condition of the atmosphere at a particular time and place. Today's temperature and yesterday's rainfall and tomorrow's wind. Climate is the statistical average of weather over long periods, the characteristic patterns of a region, the typical seasonal progression, the likelihood of extremes, and climate was changing, warming globally, though not uniformly, with polar regions warming faster than the tropics, and nighttime temperatures rising more than daytime temperatures, and the warmest days becoming warmer, while the coldest days became less cold. This warming began to show up in weather patterns, heat waves becoming more intense and lasting longer, heavy precipitation events becoming more frequent as a warmer atmosphere held more moisture, hurricanes potentially becoming more intense as they drew energy from warmer ocean waters. Meteorologists found themselves needing to become climatologists too, needing to understand not just what the atmosphere was doing today, but how the baseline was shifting, how the statistics were changing, how a warming world altered the context in which daily weather unfolded. The tools continued to evolve. Doppler radar became standard in the 1990s, measuring not just precipitation intensity, but also wind velocity within storms, allowing forecasters to detect rotation inside thunderstorms, to issue tornado warnings with greater lead time and accuracy. Weather satellites moved from polar orbits that viewed each location only twice daily to geostationary orbits where satellites hovered over the same spot on the equator, providing continuous monitoring, images every 15 minutes or faster, allowing forecasters to watch storms develop and intensify in near real time. Computer models grew more sophisticated, moving from grid spacing of hundreds of kilometers to tens of kilometers to just a few kilometers, resolving individual thunderstorms rather than just large-scale systems, running ensemble forecasts that calculated multiple possible futures to quantify uncertainty, and the Internet transformed how weather information reached people. No longer did forecasts arrive only through newspaper or television. Now anyone could access radar images, satellite loops, hourly forecasts, warnings, all updated continuously. The atmosphere's current state available at any moment on any device. The early 21st century brought an explosion of observational data from new satellite instruments, from networks of surface sensors, from commercial aircraft equipped with meteorological instruments that reported temperature and wind at cruising altitude, from wind profilers and lightning detection networks and coastal radar installations. All this data flowed into forecast models, billions of observations every day, assimilated through complex mathematical techniques into a coherent picture of the atmosphere's current state, the initial conditions from which predictions were computed, and the forecasts kept improving. 7-day forecasts in the 21st century were as accurate as 3-day forecasts had been in the 1980s. Hurricane track forecasts improved dramatically. Tornado warning lead times increased. Winter storm predictions became reliable days in advance. Yet for all the progress, for all the satellites and supercomputers and sophisticated understanding, the atmosphere retained its essential mysteriousness, its capacity for surprise. Small errors in initial conditions still grew exponentially in forecast models. Chaos, in the mathematical sense, where tiny uncertainties multiplied until predictions became meaningless beyond a certain time horizon, roughly 10 days for large-scale patterns, less for small-scale phenomena like individual thunderstorms. This fundamental limit, discovered in the 1960s by meteorologist Edward Lorenz, meant that perfect prediction was impossible, that weather would always hold some element of uncertainty, some resistance to complete knowing. Lorenz had been running a simple computer model of atmospheric convection, and one day he restarted a simulation from the middle, entering what he thought were the same initial conditions, but he had rounded the numbers slightly, entering point 506 instead of point 506,127, a difference of 1 part in several thousand. The two simulations started almost identically, but diverged slowly at first, then dramatically, until they bore no resemblance to each other at all. This sensitivity to initial conditions, later popularized as the butterfly effect, the idea that a butterfly flapping its wings in Brazil might ultimately influence whether a tornado forms in Texas, meant that perfect weather prediction would require perfect knowledge of every molecule in the atmosphere, something forever beyond reach. And so meteorology learned to live with uncertainty, to quantify it, to communicate it, to run many forecasts with slightly different initial conditions and see how much they differed, to give probabilities rather than certainties, to acknowledge the limits of prediction while still pushing those limits further every year. The science matured into something both powerful and humble, capable of seeing hurricanes days before they struck, of tracking winter storms across continents, of understanding the mechanisms that drove weather from planetary scale to cloud scale, yet always aware of how much remained unknown, how much complexity still hid in the equations, how the atmosphere continued to produce phenomena that surprised even the most experienced forecasters. And through all of this, through all the technological advancement and theoretical sophistication, the fundamental act of meteorology remained unchanged, watching the sky, noting what it does, trying to understand why, trying to anticipate what comes next. The instruments have grown more precise, the theories more complete, the forecasts more accurate, but the subject remains the same. This envelope of air wrapped around a spinning planet, heated unevenly by a star, set into motion by that heating, cycling water from ocean to cloud to rain to ocean, never still, never finished, never twice the same. And perhaps this is what makes meteorology so compelling, not just as science but as practice, as daily encounter with the world's fundamental restlessness. Every morning, somewhere, a forecaster sits before screens glowing with data, satellite images cycling, radar sweeping, model outputs scrolling, and tries to discern what the atmosphere will do today, tomorrow, this week. It is part science and part art, reading patterns in the data the way a musician reads a score, seeing not just the notes but the melody, not just the numbers but the story they tell about rising air and falling pressure and moisture, streaming northward from tropical seas. There is beauty in a well-organized low-pressure system, the way the comma-shaped cloud shield wraps around the center, the way the fronts extend outward like arms reaching, the way the whole structure rotates slowly, gracefully, like something choreographed. There is drama in a developing thunderstorm, watching on radar as a modest echo suddenly intensifies, as rotation appears in the Doppler velocity data, as the storm takes on that particular structure that means it has become dangerous, that it now carries within it the possibility of a tornado, and warnings must be issued, and people must take shelter. There is quiet satisfaction in a forecast that verifies when the predicted temperature matches the observed, when the rain begins when expected and ends when anticipated, when all the complexity of atmospheric physics resolves into an outcome you correctly anticipated, not through luck, but through understanding, and there is humility in the forecasts that fail, when the storm track shifts unexpectedly, when the rain-snow line sets up 50 miles north of where every model suggested, when conditions that seemed certain prove uncertain after all. The atmosphere teaches patience because it operates on its own schedule, not human time. A hurricane may take 2 weeks to develop from a tropical wave to a major storm. A tornado may form and dissipate in 20 minutes. A drought may persist for years, and none of these processes can be hurried or delayed by human desire. It teaches attention because the signal is often subtle, a slight veering of the wind, a small drop in pressure, a change in cloud texture that suggests instability aloft. And these small signs matter. They are the language the atmosphere speaks to those who learn to listen. It teaches interconnection, because nothing in the atmosphere happens in isolation. The temperature here depends on the wind there, which depends on the pressure gradient somewhere else, which depends on solar heating and Earth's rotation and the distribution of land and sea. Everything touching everything causes spreading in ripples too complex to fully trace. And in recent decades, it has taught us something else, that we are not merely observers of the atmosphere, but participants in it, that our choices about energy and land use and industrial development have become geological forces, altering the composition of air, changing the baseline against which all weather now unfolds. The carbon dioxide concentration in the atmosphere has risen from about 280 parts per million in pre-industrial times to over 420 parts per million today, a change faster than any natural variation in the past million years. And that change is altering weather patterns, shifting climate zones, intensifying some extremes while diminishing others. Meteorologists now forecast in an atmosphere different from the one their predecessors studied. Warmer, moister, more energetic, and they must factor this altered baseline into their predictions. must understand not just atmospheric physics, but human impacts on atmospheric chemistry, must communicate not just daily weather, but long-term trends. The scope has expanded from predicting tomorrow's high temperature to projecting how heat waves will change over coming decades, from tracking individual hurricanes to understanding how hurricane intensity distributions are shifting, from forecasting seasonal rainfall to anticipating how drought patterns might evolve in a warming world. Yet the core remains watching, measuring, calculating, trying to understand this fluid shell of air that makes Earth habitable, that cycles water and moderates temperature and shields us from solar radiation, that gives us blue skies and sunsets, rain for crops and wind for sailing, and occasionally storms that remind us how powerful the atmosphere is, how little control we truly have. There is something profound in standing outside before a thunderstorm, feeling the temperature drop as the outflow arrives, watching the shelf cloud advance, knowing that above you the atmosphere is in violent motion, updrafts rising at 60 miles per hour, downdrafts plunging, hail forming in the anvil cloud, electricity building between cloud and ground, all of it following physical laws that we understand, yet still wild, still untamed, still dangerous, or watching hurricane satellite imagery, seeing the eye form, the symmetry develop, the spiral bands tighten, this atmospheric heat engine extracting energy from warm ocean water and converting it to wind, to rain, to storm surge, capable of destroying cities, yet also part of Earth's climate system, part of how the planet redistributes heat from tropics to poles, necessary, natural, and increasingly influenced by the warming we have caused. The atmosphere is always teaching, always presenting new puzzles, new patterns, new questions. Why did this storm intensify so rapidly when the models suggested gradual strengthening? What feedback processes were at work? What did we miss in our understanding or our observations? Why does the jet stream sometimes get stuck in a particular pattern, creating persistent heat waves or flooding rains? What interactions between ocean and atmosphere and land surface lock the pattern in place? How exactly do ice crystals form in clouds? What processes govern whether a storm produces rain or snow or freezing rain? How do aerosols affect cloud development and precipitation efficiency? The questions never end, because the atmosphere's complexity is inexhaustible. Every answer reveals new questions. Every solved problem points toward unsolved ones. And so meteorology continues, this centuries-long project of understanding the sky, building on Aristotle's observations and Torricelli's barometer, and Bjerknes's fronts and Lorentz's chaos, adding new tools and techniques and insights, improving forecasts and expanding understanding, but never complete, never finished, always reaching toward fuller knowledge of this essential element in which we live. The evening is settling now, and the clouds that have been building all day are beginning to organize, beginning to show structure, dark bases and bright edges catching the last sunlight. The barometer has fallen steadily through the afternoon, the pressure dropping as the low-pressure system approaches, and the wind has shifted, backing from south to southeast, a sign that the warm front is near. Soon the rain will begin, steady rain, stratiform precipitation from clouds that span hundreds of miles, moisture that evaporated from the Gulf of Mexico day ago, that rose into the atmosphere and traveled northward on southerly winds, that will fall here tonight and seep into soil and flow into streams and eventually make its way to the ocean again, completing one more cycle in the endless circulation. And somewhere, a forecaster is watching this system, monitoring its progress, comparing observations to model predictions, preparing to update the forecast, continuing the work of reading the atmosphere, interpreting its signals, anticipating its next move. The work that began with ancient observers watching clouds and wind, that continued through centuries of instrument development and theory building, that accelerated with computers and satellites and radar, that goes on tonight and every night in forecast offices around the world, this patient effort to understand what the sky will do. It is work that matters because weather touches everything: agriculture and transportation, energy demand and water supply, outdoor events and indoor comfort, safety and planning, and the simple question of whether to carry an umbrella tomorrow. But perhaps it also matters for another reason, because paying attention to weather means paying attention to the world, noticing the wind and clouds, feeling temperature changes, watching the sky's endless variations, being present to this dynamic atmosphere that surrounds us. And in that attention, there is a kind of wonder, a recognition of the beauty and complexity of physical processes playing out overhead, invisible mostly, noticed only in their effects, but always there, always in motion, always unfolding according to laws we increasingly understand but can never fully master. The rain is beginning now. First drops tapping against windows, then steady, soaking into ground that needs it. Welcome rain from clouds that formed according to principles of thermodynamics and fluid dynamics, that were seeded by dust particles lifted from distant deserts, that grew and merged and organized into this system that a forecaster predicted days ago. And it will rain through the night, and tomorrow the front will pass, and the cold air will arrive, and the sky will clear, and the cycle will continue as it always has, as it always will, the atmosphere breathing, circulating, never still, never finished. The rhythm of weather, the pulse of the planet, continuing, always continuing. I stand at the edge of an ancient pathway where the dust holds memories of 10,000 footsteps, and the wind carries whispers from another time. This is a place where the earth itself seems to remember, where every stone has witnessed the passage of merchants and monks, of soldiers and scholars, of dreamers who carried silk and spices across impossible distances. The ground beneath feels worn smooth by centuries of movement, polished by the feet of camels and horses, by the wheels of carts laden with treasures from distant lands. The light here has a particular quality, soft and golden as it filters through the dry air, illuminating particles of dust that dance and swirl like tiny amber stars. Each grain catches the sun and becomes luminous, a small constellation suspended in the vastness between earth and sky. The landscape stretches away in gentle undulations, ochre and sienna and pale gold, punctuated by the darker shapes of distant mountains that rise like silent guardians along the horizon. There is a hush here, not silence exactly, but a kind of profound quiet that holds within it the echo of many voices. The wind moves across the open spaces with a sound like distant water, or like silk sliding across silk, a susurration that seems to carry fragments of languages I cannot quite identify, Persian and Sogdian, Chinese and Arabic, Turkic tongues and the musical syllables of Sanskrit, all blending into a chorus that speaks of connection rather than division. I notice how the pathway curves gently away, disappearing into the shimmer of heat and distance. This is not a single road, but rather a network, a web of routes that branch and reconnect, that diverge and converge like the tributaries of some vast invisible river flowing between civilizations. Some paths follow the bases of mountain ranges, seeking the precious water that emerges from melting snows. Others strike out across seemingly endless plains of grass and scrub, while still others thread through narrow valleys where the walls rise steep and protective on either side. The vegetation here tells its own story. Hardy grasses bend in the breeze, their seed heads catching light. Tamarisk trees cluster near a distant water source, their feathery branches creating pools of shade. In the far distance, a grove of poplars marks what must be an oasis, a place where underground springs bring life to the surface. These green havens were measured not in miles but in days of travel, each one a promise of survival, a guarantee that the journey could continue along the pathway. I can see the remains of structures that once offered shelter, mud brick walls worn by wind and time, their corners softened into curves, their surfaces textured by centuries of weather. These were caravans erais, waypoints in the great network of exchange, places where travelers could find protection from bandits and storms, where animals could be watered and goods could be traded, where stories could be shared across cultures and languages. Each one was built with thick walls and a single fortified entrance, designed to protect the precious cargo within, to safeguard the silk and jade, the lapis lazuli and frankincense, the manuscripts and musical instruments that moved between empires. I think about the goods that traveled these routes, bolts of silk so fine they seemed to capture moonlight in their weave. Each length represented months of labor, the careful cultivation of mulberry trees, the tending of silkworms, the patient work of reeling and spinning and dyeing and weaving. The silk moved westward in bundles wrapped in protective cloth, and with it moved ideas about artistry and technique, about color and pattern, about what it meant to create something of surpassing beauty. But the exchange flowed in both directions. Glassware from Roman workshops made the journey eastward, each piece a marvel of transparency and color, vessels that seemed to hold light within their curves. Gold coins bearing the profiles of distant emperors circulated along these routes, carrying with them images of power and authority, symbols of legitimacy that crossed cultural boundaries. Spices came from lands to the south, cinnamon and cardamom, pepper and cloves, each one commanding prices that seem almost incomprehensible, valued sometimes at weights equivalent to gold or silver. The pathway winds through landscapes of extraordinary diversity. From the markets of Chang'an, now known as Xi'an, where the eastern terminus bustled with activity, the routes spread westward across the territories of Imperial China, beyond the protective barrier of the Great Wall. The paths entered regions of shifting allegiances, where oasis cities maintained their independence through careful diplomacy and strategic location. Each city was a world unto itself. Dunhuang, with its cave temples filled with sacred art, Turfan nestled in its depression below sea level, Kashgar at the foot of the Pamirs, where routes divided, one path heading southwest toward India and Persia, another continuing westward toward the Mediterranean. The journey required patience measured in months and years. A single caravan might take more than a year to traverse the entire distance from one end to the other, though few attempted such an epic undertaking. More commonly, goods changed hands multiple times, passing through a chain of merchants, each one adding their own margin, each transaction a small node in the vast network of exchange. The economics of this trade were complex, shaped by distance and danger, by scarcity and desire, by the simple human longing for novelty and beauty. I imagine the night sky above these routes, so clear and dark away from cities. The stars would have been impossibly bright, the Milky Way, a river of light stretching overhead. Travelers navigated by these celestial markers, learning to read the positions of constellations, to mark the passage of seasons by the rising and setting of particular stars. The moon would have been both companion and timekeeper, its phases marking the passage of days, its light turning the desert into a landscape of silver and shadow. The origins of these pathways reach back into depths of time that seem almost mythological, yet they are grounded in the very practical needs of empires and the human desire for things that existed only in distant lands. Long before the routes became the organized network we might imagine, there were scattered trails, tentative connections between neighboring regions, small exchanges that gradually extended their reach. In the 2nd century before the Common Era, the Han dynasty of China had consolidated its power, establishing an empire of remarkable sophistication and reach. The emperor sat in his palace in Chang'an, surrounded by the trappings of civilization, silks and lacquerware, bronze vessels and jade ornaments. Yet beyond the western frontiers lay territories unknown and unsecured, lands inhabited by peoples the Chinese called the Xiongnu, nomadic confederations whose cavalry posed a constant threat to the settled agricultural communities of the empire. The Emperor Wu, who would reign for more than 50 years, recognized that military strength alone might not be sufficient to guarantee security. He conceived of a different strategy, one that required knowledge of the lands beyond his borders, understanding of potential allies who might help encircle the Xiongnu threat. And so in the year 139 before the Common Era, he dispatched a courtier named Zhang Qian on a mission westward, a journey that would become legendary in the annals of exploration. Zhang Qian set out with a company of perhaps 100 men. Their objective was to reach a people called the Yuezhi, who had been driven westward by the Xiongnu and were said to harbor resentment against their former enemies. The journey would take Zhang Qian through territories controlled by the very people he sought to circumvent, and perhaps inevitably he was captured by the Xiongnu, held for 10 years in a captivity that was, by some accounts, not unduly harsh. He was given a wife, allowed to establish a household, yet remained a prisoner nonetheless. When Zhang Qian finally escaped, he did not return home, but continued westward in pursuit of his original mission. He traveled through the kingdoms of Central Asia, through Fergana with its famous heavenly horses that sweated what appeared to be blood, through Sogdiana with its merchant cities. He reached Bactria, the land where Greek influence still lingered from the conquests of Alexander more than a century before. He observed irrigation systems and agricultural techniques, cities and fortifications, trade goods and cultural practices entirely foreign to his experience. The Yuezhi, when he finally found them, showed little interest in forming a military alliance against the distant Xiongnu. They had established themselves in new territories and had no desire to revisit old conflicts. Yet Zhang Qian's journey was far from fruitless. He returned to China after an absence of 13 years, bringing with him knowledge that would transform his empire's understanding of the world beyond its borders. His reports described lands of astonishing richness and variety, kingdoms with populations numbering in the hundreds of thousands, cities with markets that bustled with goods from distant regions. He spoke of grapevines and alfalfa, of techniques for breeding superior horses, of precious stones and metals. His accounts opened the imagination of the Han court to possibilities of trade and exchange that had previously existed only as rumors and speculation. The response was gradual but transformative. Chinese envoys began to travel westward with increasing frequency, carrying gifts of silk, which soon became the most desired commodity in the western lands. The silk production of China was a closely guarded secret, a mystery that would remain unsolved in the West for centuries. The fabric itself seemed almost magical, lighter than linen, more lustrous than wool, capable of being dyed in colors of extraordinary vibrancy. It draped beautifully, moved like water, and possessed a subtle sheen that caught light in ways that seemed almost alive. For the Han Dynasty, silk became a form of currency, a diplomatic tool as valuable as any army. Bolts of silk could secure alliances, purchase peace, demonstrate the superiority of Chinese civilization. The emperor's workshops produced silk in vast quantities, yet demand seemed inexhaustible. To the west, in the lands controlled by the Parthian Empire, silk commanded prices that made the long journey profitable. Despite the dangers and difficulties, the Parthians occupied a crucial position in this emerging network of exchange. Their territory stretched from the edges of Roman influence in the west to the borders of the Kushan Empire in the east. They controlled the routes through Persia, the pathways that funneled goods between the Mediterranean world and the lands beyond. And they recognized the value of their position, serving as middlemen who profited from both directions of trade, purchasing silk from Eastern merchants and selling it to Western buyers at prices that reflected the distance and mystery of its origins. In Rome, silk became a symbol of luxury that prompted both desire and moral concern. Roman writers complained about the expense of silk, about the drain of gold eastward to pay for this exotic fabric. Pliny the Elder calculated that the empire spent 100 million sesterces annually on imports from the East, a figure that scandalized those who saw it as evidence of decadence and weakness. Yet the demand continued unabated. Roman senators wore togas trimmed with silk. Wealthy women draped themselves in silk garments that scandalized conservative observers with their revealing translucency. But silk was far from the only commodity that moved along these routes. Horses traveled eastward from Fergana, animals of a superior size and strength that the Chinese called heavenly horses, believing them descended from supernatural stock. The Han Dynasty mounted military expeditions specifically to acquire these horses. Recognizing their value for cavalry warfare, a fine horse from the western regions could command a price equivalent to many bolts of silk, and breeding programs sought to incorporate their bloodlines into Chinese herds. Jade moved eastward along northern routes from the deposits near Khotan, stones of white and green that Chinese craftsmen valued above gold. The material was believed to possess spiritual properties, to connect the earthly realms with the celestial. Jade burial suits were constructed for emperors, each suit requiring thousands of carefully shaped plaques sewn together with gold or silver wire, a task that might occupy craftsmen for years. Glass traveled eastward from Roman and Persian workshops. Vessels and beads that seemed to capture light and color in their transparent depths. For Chinese artisans familiar with jade and bronze, with lacquer and ceramic, glass represented an entirely different aesthetic. Its clarity and luminosity offered new possibilities for artistic expression. Roman glassware has been found in tombs dating to the Han Dynasty, evidence of how far these precious objects traveled and how highly they were valued. Gold and silver moved in both directions, not just as raw metal, but as worked objects. Roman coins reached China, where they were sometimes melted down, sometimes kept as curiosities. Persian silverware with its distinctive designs appeared in Chinese collections, while Chinese bronze mirrors traveled westward, their polished surfaces capable of reflection, their backs decorated with intricate patterns and cosmological symbols. The routes themselves were not lines but networks, pathways that branched and reconnected based on season and safety, water availability and political conditions. From Chang'an, travelers might follow the Hexi Corridor, a relatively narrow passage between mountains and desert that funneled traffic westward. The corridor was studded with garrison towns, military outposts established to protect travelers and maintain Han control over this strategic territory. At Dunhuang, the routes divided. One path headed northwest toward the Tian Shan Mountains, following a series of oasis towns, Hami and Turfan, Kucha and Aksu, before reaching Kashgar at the western edge of the Tarim Basin. Another route curved southwest, skirting the southern edge of the Taklamakan Desert, passing through Miran and Nia, Khotan and Yarkand, also converging at Kashgar. The choice between routes might depend on political conditions, on which cities offered more favorable terms for trade, on where water was more reliably available. Beyond Kashgar, the paths crossed the Pamir Mountains, the roof of the world, where altitude and cold tested the endurance of travelers and pack animals. The passes reached heights of more than 15,000 feet, where the air grew thin and breathing became labored, where snow might fall even in summer months. Those who survived the crossing descended into the valleys of Sogdiana, into lands where Persian cultural influence mingled with Greek architectural traditions, where Buddhism was beginning to spread from its origins in India. The cities of Sogdiana, Samarkand, and Bukhara became crucial nodes in the network of exchange. Their merchants developed expertise in long-distance trade, learning multiple languages, understanding the preferences and customs of different markets. Sogdian communities established themselves along the routes, creating networks of trust that facilitated commerce. A Sogdian merchant in Chang'an could correspond with relatives in Samarkand, could arrange for goods to be held or transported, could access credit based on relationships that spanned thousands of miles. These early centuries of contact established patterns that would persist for hundreds of years. The exchange was never merely commercial. Ideas traveled with goods. Technologies crossed borders embedded in objects or carried in the minds of craftsmen. A Chinese artisan examining a piece of Roman glass might begin to experiment with similar techniques. A Persian metalworker might incorporate design elements seen on Chinese bronzes. The roots became conduits not just for objects but for knowledge, for techniques, for aesthetic sensibilities that would influence artistic traditions across the breadth of Eurasia. Religious ideas found particularly fertile ground along these routes. Buddhism, which had emerged in northern India in the 6th century before the Common Era, began to spread along the trade routes into Central Asia and eventually into China. Missionaries and monks traveled the same paths as merchants, sometimes in the company of caravans, seeking the protection that numbers provided. The oasis cities became centers of Buddhist learning, their cave temples carved into cliff faces, decorated with murals that blended Indian, Persian, and local artistic traditions into something new and syncretic. The routes also carried Zoroastrianism westward from Persia, Manichaeism, which combined elements from multiple traditions, Christianity in its Nestorian form, which found adherents in Central Asia and eventually in China itself. Each religion adapted to local conditions, incorporated local deities and practices, created hybrid forms that might be almost unrecognizable to adherents in their lands of origin. By the end of the 1st century of the Common Era, the basic infrastructure of exchange was established. The routes were known, the cities and caravanserais marked, the risks were understood, as were the potential rewards. Empires had recognized the value of controlling and protecting these pathways, of taxing the commerce that flowed through their territories. The Kushan Empire, which had emerged from the Yuezhi peoples Jiang Qian had sought centuries before, controlled crucial territory in what is now Afghanistan and northern India. They minted coins that bore Greek inscriptions on one side and Indian on the other, a perfect symbol of their position at the crossroads of cultures. The Kushan coins circulated widely, becoming a common medium of exchange across vast distances, accepted in markets from the Ganges Valley to the oasis cities of the Tarim Basin. Their gold dinars were minted to a standard weight, recognizable and trusted, a physical manifestation of the connections that bound distant regions into a single economic sphere. During the 2nd and 3rd centuries of the Common Era, the trade reached a kind of apex, a period when the major empires maintained relative stability and the routes flourished with activity. The Han Dynasty in China, though entering its later phases, still commanded resources sufficient to protect and promote commerce. The Kushan Empire served as a bridge between East and West. Their control of mountain passes and strategic valleys, making them essential partners in any long-distance exchange. The Parthian Empire, and later the Sasanian Empire that would supplant it, maintained control over the Iranian plateau, while Rome at its height extended from Britain to Mesopotamia, creating a zone of relative peace and security that facilitated movement. The caravans that moved along these routes were impressive undertakings, requiring organization and resources that only wealthy merchants or state enterprises could muster. A typical caravan might include anywhere from 50 to several hundred camels, each animal capable of carrying loads of 300 to 400 pounds. The Bactrian camel, with its 2 humps and thick coat, was perfectly adapted to the harsh conditions of Central Asian travel, able to go for days without water, to survive on the sparse vegetation of desert margins, to endure temperature extremes that would kill horses or mules. The caravans moved slowly, covering perhaps 20 to 30 miles in a day, sometimes less, when terrain was difficult or weather unfavorable. The pace was determined by the animals, by the need to reach water sources, by the desire to arrive at way stations before nightfall, when the dangers of travel multiplied in darkness. A journey from Chang'an to the Mediterranean might take a year or more, and few caravans attempted the entire distance. Instead, goods changed hands multiple times, each transaction occurring in the markets and caravanserais that punctuated the routes. Life within a caravan followed rhythms dictated by survival and commerce. The day began before dawn, when the relative cool made loading and preparation less arduous. Animals were watered and fed, loads were secured and balanced. The caravan leader, often a man of considerable experience and local knowledge, would determine the day's destination, choosing routes based on intelligence about conditions ahead, about the political situation in territories they would cross, about where water could be reliably found. As the sun climbed higher, the landscape transformed. Colors that had seemed muted in dawn light became vivid and harsh. The sky turned a blue so deep it seemed almost solid, unmarked by clouds in the dry air. Heat rose from the ground in visible waves, distorting distant features, creating mirages that promised water where none existed. The silence of these spaces could be profound, broken only by the sounds of the caravan itself, the soft padding of camel feet, the creak of leather and wood, the occasional call of a handler to his animals. The goods they carried represented enormous value, concentrated wealth that made caravans attractive targets for bandits and raiders. Silk was particularly valuable relative to its weight, making it ideal for long-distance trade despite the dangers. A single camel might carry silk worth many times the animal's own value. Merchants developed elaborate strategies to protect their investments, traveling in large groups for safety, paying tribute to local powers for safe passage, hiring guards and scouts, developing relationships with communities along the routes who could provide intelligence about dangers ahead. The caravanserais that dotted the routes were more than simple inns. They were fortified compounds designed to provide security and facilities for both travelers and their animals. The architecture followed similar patterns across vast distances. A single gate that could be barred against intruders, thick walls that enclosed a central courtyard, rooms arranged around the perimeter for human habitation. The courtyard provided space for animals to be penned safely, for goods to be unloaded and inspected, for merchants to conduct business and negotiate deals. Inside a caravanserai, the atmosphere combined commerce and culture in ways unique to these crossroads. Merchants from different regions would gather, speaking different languages, wearing different styles of dress, worshiping different gods. Yet they shared common interests in trade and profit, in safe passage and favorable markets. They exchanged information as readily as goods, news from distant regions, intelligence about political changes, knowledge about new routes or abandoned cities, about harvests and famines, about wars and alliances. The cities that thrived along these routes developed distinctive characters shaped by their position and prosperity. Samarkand, strategically located in the Zaravshan Valley, became renowned for its gardens and its architecture, for the skill of its craftsmen in working metal and glass. The city drew water from the river and from an extensive network of irrigation channels, creating an island of fertility in an otherwise arid landscape. Its markets displayed goods from across the known world. Chinese silk and Indian gems, Persian metalwork and Roman glass, local products including paper manufactured using techniques learned from Chinese prisoners of war captured in the 8th century. Merv, located in what is now Turkmenistan, grew to become one of the largest cities in the world during its peak. Its population may have reached several 100,000, sustained by sophisticated irrigation systems that brought water from the Murghab River to fields and gardens surrounding the urban core. The city was ringed by walls of impressive height and thickness, protection against the nomadic peoples who periodically swept down from the northern steppes. Within those walls, scholars and scientists pursued knowledge. Astronomers calculated the movements of celestial bodies. Mathematicians developed new techniques. Physicians compiled medical knowledge drawn from Greek, Indian, and Persian sources. The process of exchange itself involved complexities that went far beyond simple buying and selling. Different regions used different currencies, different systems of weights and measures. Language barriers required interpreters, men who could navigate not just between tongues but between cultural assumptions and commercial practices. Trust was essential, yet difficult to establish between strangers from vastly different backgrounds. Mechanisms evolved to address these challenges. Letters of credit allowed merchants to access funds in distant cities without transporting actual precious metals. Partnerships spread risk across multiple investors. Contracts specified terms in elaborate detail, attempting to account for the many uncertainties inherent in long-distance trade. The goods themselves often underwent transformation during their journeys. Silk might be purchased as raw thread in China, woven into fabric in Sogdiana, dyed in Persia, and finally tailored into garments in Rome. Each stage added value. Each transformation involved skilled artisans applying techniques developed over generations. A piece of lapis lazuli might be quarried in the mountains of Badakhshan, transported to a cutting center where it would be shaped and polished, then carried further to be incorporated into jewelry or decorative objects. Its deep blue color, sometimes flecked with gold pyrite, made it prized for both aesthetic and symbolic purposes. Spices represented perhaps the most remarkable aspect of the luxury trade. Pepper from southern India, cinnamon from Ceylon, cloves from the islands of Southeast Asia. These products came from regions far beyond the main Silk Road routes, reaching the trading networks through the maritime connections and southern pathways. Yet their value was such that they circulated widely. A pound of pepper might be worth as much as a pound of silver in some markets. Cinnamon commanded prices that made the dangerous sea journey to obtain it worthwhile. The spices themselves were used not just for flavoring food, but for medicine, for religious rituals, for preserving meat in an age before refrigeration. The maritime routes that connected with the overland Silk Road created a complementary network of exchange. Ships sailed from ports on the Red Sea and the Persian Gulf, following monsoon winds across the Indian Ocean to ports on the west coast of India. Some continued further, reaching Ceylon and eventually the coasts of Southeast Asia. The monsoon winds were remarkably predictable, blowing from the southwest during summer months, reversing to blow from the northeast in winter. Sailors learned to time their voyages to these seasonal rhythms, departing with one monsoon and returning with the next, a round trip that might take a year or more. These sea routes carried many of the same luxury goods as the overland paths, but they also transported bulk commodities that were too heavy or bulky for camel caravans. Grain moved by ship, as did timber and metals. Ceramic vessels traveled in enormous quantities. Chinese porcelain eventually becoming a major export. Its translucent quality and fine decoration made it highly desirable, while its durability made it suitable for long sea voyages, despite the obvious risks of breakage. The cultural exchanges facilitated by these routes of trade were perhaps even more significant than the commercial transactions. Technologies spread across Eurasia. Paper manufacturing, which originated in China, gradually moved westward, reaching Central Asia by the 8th century, the Islamic world by the 9th, and Europe by the 12th. And the impact of this technology on literacy, on record keeping, on the transmission of knowledge cannot be overstated. Each region adapted paper making to local conditions and materials, creating variations in quality and characteristics. Agricultural products and techniques also traveled through these routes. Grapes and alfalfa, which Zhang Qian had observed in Fergana, were successfully introduced to China, transforming agricultural practices in some regions. Cotton cultivation spread from India westward and eastward, eventually becoming established across a wide geographic range. The stirrup, a seemingly simple innovation that revolutionized cavalry warfare, may have originated in Central Asia before spreading both east and west, fundamentally changing military tactics and the balance of power between infantry and mounted forces. Artistic styles and motifs circulated along these routes, creating fusion traditions that blended elements from multiple sources. Buddhist art in Central Asia incorporated Hellenistic elements inherited from the Greek kingdoms that had once existed in the region. Indian artistic conventions merged with Persian and Chinese influences. The result was styles of remarkable beauty and complexity, visible in the cave temples carved into cliff faces along the routes. Dunhuang and Bezeklik, Kizil and Bamiyan, each site preserving murals and sculptures that demonstrate the creative synthesis possible when diverse traditions encounter one another. Musical instruments traveled thus through these routes. The lute, which would become fundamental to both Middle Eastern and European musical traditions, may have originated in Persia before spreading in multiple directions. Chinese artisans adopted and adapted instruments from Central Asia, while Central Asian musicians incorporated elements of Chinese musical theory and practice. The result was a rich tapestry of musical exchange, where melodies and rhythms moved across cultural boundaries, transformed and reinterpreted in each new context. The transmission of medical knowledge followed similar patterns. Greek medical texts were translated into Persian and Arabic, their ideas about the humors and about treatment protocols spreading eastward. Indian Ayurvedic traditions influenced medical practice in Central Asia and beyond. Chinese medical concepts, including acupuncture and herbal pharmacology, became known in the West through travelers and texts. Physicians along the trade routes had access to materia medica from across Eurasia, allowing them to experiment with treatments and remedies unknown in their regions of origin. The exchange of medical knowledge represented just one thread in a vast tapestry of intellectual transmission. Mathematical concepts traveled along these routes. Indian numerals, including the revolutionary concept of zero as both placeholder and number, moved westward through Persian intermediaries, eventually reaching Europe, where they would transform calculation and commerce. Chinese mathematical treatises sometimes found their way into Central Asian libraries, while Greek geometric traditions influenced scholars across multiple cultures, but the roots that had facilitated such remarkable exchange were never stable, never guaranteed. They existed in a state of constant flux, shaped by forces both human and natural. Political instability could render entire sections impassable. A change of dynasty in China might bring internal turmoil that disrupted trade. The collapse of central authority could leave merchants without protection, vulnerable to bandits and local warlords who extracted tribute or simply seized goods by force. The 3rd century brought particular challenges. The Han Dynasty finally collapsed in the year 220, fragmenting into rival kingdoms that competed for supremacy. The period that followed, known as the Three Kingdoms and then the Six Dynasties, saw China divided and often at war with itself. The central authority that had maintained garrison towns along the Hexi corridor weakened, making the eastern portions of the routes more dangerous and less reliable. In the west, the Roman Empire faced its own crisis. The 3rd century witnessed rapid succession of emperors, many of whom met violent ends. Provincial armies fought each other for supremacy. Border defenses weakened, allowing increased incursions by peoples beyond the frontiers. The economic disruption reduced demand for luxury imports, while the political chaos made long-distance trade more hazardous. The Sasanian Empire, which had replaced Parthian rule in Persia, fought extended wars with Rome, and these conflicts often occurred precisely in the territories through which trade routes passed. Yet even during these troubled centuries, the exchange continued, albeit in reduced volumes and through adjusted pathways. The routes proved remarkably resilient, adapting to new political realities, finding alternative passages when traditional ones became blocked. Merchants developed relationships with new powers, paid new tribute to new authorities, adjusted their strategies to changed circumstances. The basic infrastructure remained: the knowledge of routes and water sources, the caravanserais that still offered shelter even when empires crumbled. The rise of new powers brought renewed vitality to portions of the network. The Gupta Empire in India, beginning in the 4th century, presided over a golden age of art and learning. Its stability and prosperity attracted trade, making the southern routes through India increasingly important. Buddhist institutions flourished under Gupta patronage, creating great centers of learning that drew scholars from across Asia. The university at Nalanda became renowned, its libraries holding thousands of manuscripts, its teachers instructing students in logic and medicine, astronomy and philosophy. In Central Asia, the Hephthalites, sometimes called the White Huns, established control over significant territories. Their rule disrupted some traditional patterns, but created new opportunities for those willing to adapt. They minted coins and maintained cities, collected taxes, and protected certain routes. The Sogdian merchants, with their remarkable adaptability, continued to flourish, establishing communities across an even wider geography. Their letters, preserved by chance in the dry climate of the Tarim Basin, reveal the concerns and calculations of traders managing far-flung commercial operations. The 6th century witnessed the emergence of a new power that would transform the political and cultural landscape of Central Asia and beyond. The Turkic peoples, moving westward from the Mongolian steppes, established a khaganate of vast extent. Their cavalry armies were formidable, their leaders shrewd. They recognized the value of controlling trade routes, of taxing caravans, of facilitating exchange from which they could extract revenue. Under Turkic rule, portions of the Silk Road experienced renewed security and activity. China's reunification under the Sui dynasty in the late 6th century, followed by the Tang dynasty's rise in the early 7th century, brought a new golden age to the eastern portions of the routes. How the Tang capital at Chang'an grew to become perhaps the largest city in the world, its population reaching over 1 million. The city was cosmopolitan in a way unprecedented in Chinese history. Sogdian merchants maintained their own quarters. Persian Zoroastrians built fire temples. Nestorian Christians established churches. Muslims would later construct mosques. The Tang emperors actively promoted trade, establishing formal diplomatic relations with kingdoms across Central Asia and beyond. Embassies arrived bearing tribute and gifts, while Chinese missions traveled westward. The famous Buddhist monk Xuanzang journeyed to India in the 7th century, seeking authentic Sanskrit texts. His return after 16 years, carrying hundreds of manuscripts, became legendary. His account of his travels provided detailed information about the regions he traversed, the peoples he encountered, the religious practices he observed. During this Tang period, the routes carried unprecedented volumes of trade. Silk production had reached new heights of sophistication, with techniques for creating complex patterns and for combining silk with gold thread. Chinese ceramics, particularly the distinctive three-color glazed pottery, became export items of significant value. Tea, which had been consumed in China for centuries, began to spread westward, though it would be many more centuries before it became widely popular in Europe. Yet even this flourishing period contained seeds of change. The rise of Islam in the 7th century transformed the political and cultural landscape of Western Asia. Arab armies swept across Persia, defeating the Sasanian Empire. They pushed into Central Asia, bringing a new religion and a new political order. Initially, this might have seemed disruptive to trade, but Islam proved remarkably conducive to commerce. The Quran contained detailed regulations about contracts and commerce, about fair dealing and the prohibition of certain practices. Muslim merchants would become crucial participants in the trade networks, eventually dominating certain routes. The 8th century brought crisis to Chinese control of Central Asia. The An Lushan rebellion, beginning in 755, devastated the Tang Empire. The rebellion lasted for years, causing massive casualties and economic disruption. In its aftermath, Tang power in Central Asia contracted. Tibetan forces moved into territories previously under Chinese control. The Uyghurs, a Turkic people who had converted to Buddhism and Manichaeism, established their own kingdom in the Tarim Basin. The balance of power had shifted, and with it the patterns of trade. Chinese silk continued to flow westward, but now through intermediaries who were not subject to Chinese authority. The Abbasid Caliphate, with its capital at Baghdad, became a major terminus for goods from the east. Arab and Persian merchants played increasingly important roles, their networks extending from the Mediterranean to the South China Sea. They developed sophisticated banking practices, forms of credit and partnership that facilitated long-distance trade even in the absence of centralized political control. Maritime routes grew in importance relative to overland paths. Ships could carry larger cargoes than camel caravans, and while sea voyages carried their own dangers, they could be faster and sometimes more economical. The Persian Gulf became a major conduit for trade between the Islamic world and Asia. Ports like Basra and Siraf grew wealthy from commerce. Chinese ceramics and silks arrived by sea, as did Southeast Asian spices and Indian textiles. The Indian Ocean Trade Network, with its predictable monsoon winds, offered an alternative to the overland routes through Central Asia. The land routes did not disappear, but their character evolved. The great caravanserais still sheltered travelers. The oasis cities still served as markets and way stations, but the political fragmentation of Central Asia meant that merchants faced a more complex landscape of authorities and allegiances. A journey that had once required negotiating with a handful of major powers now might involve dealings with dozens of local rulers, each extracting their own fees, each maintaining their own level of security or disorder. Religious transformations continued to reshape the cultural landscape. Buddhism, which had spread along the Silk Road into China, began a slow decline in Central Asia itself, increasingly challenged by Islam, which offered clear rules for commerce and social organization. The great Buddhist centers like Bamiyan would eventually fall to Muslim armies, their monuments sometimes destroyed, their monasteries converted or abandoned. Yet in China and further east, Buddhism had become deeply rooted, developing distinctively Chinese and then Japanese forms that would persist for centuries. The Mongol conquests of the 13th century brought dramatic changes. The armies of Genghis Khan and his successors swept across Asia, destroying cities that resisted, incorporating others into a vast empire. The initial impact was catastrophic for many communities. Samarkand and Merv, Nishapur and Baghdad all suffered devastation. Populations were massacred, irrigation systems destroyed, centuries of accumulated wealth seized or scattered. Yet the Mongol peace that followed, the Pax Mongolica, created conditions favorable to trade on an unprecedented scale. A single authority controlled territories stretching from China to Eastern Europe, allowing merchants to travel vast distances under unified protection. The Mongols actively encouraged trade. Recognizing its value as a source of revenue, they maintained roads and way stations, provided documents that granted safe passage, even operated a postal system of remarkable efficiency. European travelers like Marco Polo journeyed eastward during this period, their accounts revealing both wonder and detailed observation. Marco Polo's description of his years in the service of Kublai Khan, whether entirely accurate or embellished, captured European imagination. His reports of Chinese wealth and sophistication, of paper money and coal for fuel, of cities larger than any in Europe, sparked interest in direct contact with the East. But the Mongol Empire proved ephemeral in its unity, fragmenting into rival khanates within decades of its greatest extent. The Black Death, which may have originated in Central Asia, spread along the trade routes in the 14th century, devastating populations from China to Europe. The disease traveled with merchant caravans and ships, a deadly cargo that killed perhaps 1/3 of the population in affected regions. The demographic catastrophe disrupted trade networks, depopulated cities, created labor shortages that took generations to overcome. The maritime routes continued to grow in importance. Chinese fleets under the Ming dynasty, led by the Admiral Zheng He, in the early 15th century sailed to Southeast Asia, India, Arabia, and East Africa, demonstrating Chinese naval capability, though these voyages would be discontinued as Ming policy turned inward. In the West, European powers were developing maritime technologies that would soon allow them to sail around Africa to reach Asia directly, bypassing the overland routes entirely. The overland Silk Road, as a primary conduit of exchange between East and West, was entering its twilight. The routes still existed, caravans still traveled them, but the great age of intercontinental trade via Central Asian pathways was drawing to a close. New patterns were emerging, maritime routes that could carry larger cargoes more economically, European colonial expansion that would create different structures of global exchange. The oasis cities would continue, but their pivotal role in connecting civilizations was diminishing. Yet what had been created over more than a millennium could not simply vanish. The languages spoken in Central Asia bore traces of centuries of contact. Persian and Turkic tongues incorporating words from Chinese and Sanskrit, from Arabic and Sogdian. The artistic traditions preserved hybrid forms, blending elements from multiple sources into distinctive local styles. The very concept of a world connected by trade, where goods and ideas could flow across vast distances, had become embedded in human consciousness, a legacy that would shape all subsequent patterns of globalization. The legacy that remained was not merely historical, not simply a matter of dates and dynasties, of trade volumes and political boundaries. It was something more fundamental, a transformation in how human beings understood their place in a connected world. Before these roots became established, civilizations existed in relative isolation, aware perhaps of distant others through rumor and legend, but without sustained contact, without the continuous exchange that makes different peoples truly knowable to one another. The Silk Road changed this, creating networks of relationship that persisted across generations. Families in Samarkand might maintain trading partnerships with families in Chang'an for centuries. Knowledge passed from parent to child, trust built over lifetimes, sustained across distances that could take years to traverse. The objects that traveled these routes carried meanings that transcended their material value. A piece of silk was never merely fabric. It was the product of thousands of hours of labor, the result of techniques refined over centuries, the manifestation of an aesthetic tradition that valued certain qualities of color and drape and pattern. When that silk arrived in Rome or Constantinople, it brought with it ideas about beauty, about what was desirable and worthy of emulation. A Roman noble wearing silk was participating, perhaps unknowingly, in a dialogue with Chinese culture, responding to its definitions of elegance and refinement. Similarly, a piece of Roman glassware arriving in China was not just a vessel, it represented an entirely different approach to material and form, a tradition of working with transparency and color that had its own long history, its own aesthetic principles. Chinese craftsmen examining such pieces might be inspired to experiment, to attempt similar effects, or they might deliberately choose different paths, asserting their own artistic values. Either way, the encounter with foreign objects prompted reflection, comparison, creative response. The religious ideas that spread along these routes demonstrate perhaps most clearly how exchange could transform. Buddhism in China became something distinct from Buddhism in India. incorporating Taoist concepts and Confucian ethics, developing new schools of thought and practice that would have been foreign to its founders, yet it remained recognizably Buddhist, maintaining core teachings even as it adapted to new cultural soil. This capacity for creative adaptation, for synthesis rather than simple replacement, characterized much of the cultural exchange along the Silk Road. Languages evolved through contact, borrowing words for new concepts, new technologies, new foods and materials that had no names in the receiving tongue. Persian acquired Chinese loan words. Chinese incorporated terms from Sanskrit and Sogdian. Arabic would eventually absorb vocabulary from the languages it encountered through conquest and trade. Each borrowed word represented a moment of contact, a recognition that the other possessed something worth incorporating, worth making one's own. The very landscape of Central Asia bears witness to these centuries of exchange. The ruins of cities and caravanserais, though often reduced to earthen mounds by time and weather, still mark the locations where merchants gathered, where goods changed hands, where different peoples encountered one another. The cave temples carved into cliff faces preserve artwork that blends traditions. Greek-influenced faces on Buddhist bodhisattvas, Persian decorative motifs framing Chinese-style landscapes, Indian compositional principles applied to Central Asian subjects. Even the genetic heritage of Central Asian peoples reflects these patterns of movement and mixture. Populations along the routes show ancestry from multiple sources, Eastern and Western Eurasian lineages mingling. The merchants and soldiers, the monks and craftsmen who traveled these routes sometimes settled far from their places of origin, married locally, raised children who inherited multiple cultural traditions. These biological connections paralleled the cultural ones, creating human bonds that linked distant regions. The concept of luxury itself was transformed by the Silk Road. Before sustained contact, luxury was local, defined by what was rare within a particular region. The trade routes created new categories of the precious, defined by distance and exoticism rather than local scarcity. A substance might be common in its region of origin, but become extraordinarily valuable when transported thousands of miles. This created economic incentives for long-distance trade, even when local alternatives existed. People were willing to pay premiums for goods from distant lands, for the status and novelty they represented. Technology transfer along these routes occurred gradually, often without any conscious intention to share knowledge. A craftsman examining a foreign object might discern its method of manufacture, experiment until achieving similar results. Techniques for papermaking, for glazing ceramics, for working metals and glass, all spread through this combination of observation and experimentation. Sometimes knowledge was deliberately sought, envoys sent to learn foreign techniques, craftsmen hired to bring their expertise to new lands. But more often, transfer happened through the slow accumulation of incremental insights, each merchant or traveler bringing back fragments of knowledge that could be pieced together. The financial innovations developed to facilitate this trade had implications far beyond the routes themselves. Letters of credit, bills of exchange, partnerships that spread risk across multiple investors. These mechanisms made long-distance trade practical even when the journeys took years. They required trust, legal frameworks, institutions that could enforce contracts across cultural boundaries. The development of such systems represented a kind of globalization avant la lettre, creating commercial relationships that transcended political divisions. Time itself seemed to operate differently along these routes. A merchant might spend years away from home, watching seasons change in foreign lands, learning to read the signs of approaching monsoons or the warnings of coming sandstorms. The rhythm of travel, measured in daily distances and seasonal opportunities, created a different relationship to temporality than settled agricultural life. One learned patience, acceptance of delays, adaptation to circumstances beyond one's control. Yet within this slow rhythm, moments of intense activity punctuated the journey. The arrival at a major market city, the negotiation of prices and terms, the excitement of learning what goods had arrived from other directions, what new opportunities might exist. These moments of connection, when information and goods and peoples converged, were the beating heart of the network, the nodes where the entire system came alive with possibility. I stand again on the pathway where this contemplation began. The light has changed, shifting from gold to amber as the day ages. The shadows have lengthened, stretching across the undulating terrain, creating patterns of light and dark that emphasize the contours of the land. The wind continues its gentle movement, carrying dust that catches the sun. These particles have their own history eroded from rocks that witnessed the passage of countless caravans, stirred by hooves and feet and wheels that no longer move. They dance in the air, following currents invisible to the eye, settling and rising in patterns that seem almost deliberate. The distant mountains remain, as they have remained for millions of years, indifferent to the human stories played out in their shadow. They mark the horizon, a reminder of constancy amid all the change. All those travelers saw these same peaks, measured their progress by their slow approach and eventual passage. The mountains absorbed their hopes and fears, their ambitions and disappointments, giving nothing back but their presence. I think about the silence that now pervades these spaces, where once there would have been the sounds of arrival and departure, of negotiation and greeting, of animals and carts, of many languages blending into a general hum of human activity. The caravanserais stand empty, open to the sky, their roofs long since collapsed, their courtyards filled with drifted sand and scattered stones, yet they remain, testimony to what once was, to the human effort invested in creating shelter and safety in harsh and distant places. The route itself is barely visible now, just a slight depression in the earth, a path worn by so much passage that the land itself remembers. In some places, modern roads follow the ancient ways, vehicles traveling routes first established by camel and horse. In others, the old paths are abandoned entirely, left to fade back into the landscape, reclaimed by time and nature. What remains is more subtle than ruins. It lives in the objects preserved in museums, silks and ceramics, coins and manuscripts, each one a messenger from the past, speaking of the hands that made it, the journey it undertook, the distance it traveled to, survive into our present. It lives in languages that still carry borrowed words, in artistic traditions that blend influences from multiple sources, in genetic lineages that trace back to these movements and mixtures. The idea of connection persists, that fundamental human impulse to reach beyond the immediate, to seek what lies over the horizon, to wonder about distant peoples and places. The Silk Road was one expression of this impulse, neither the first nor the last, but remarkable in its scale and duration, in the civilizations it linked, in the exchanges it facilitated. The sky above deepens toward evening. The blue becomes richer, more saturated. Stars will soon emerge, the same stars that guided travelers across these routes, celestial markers unchanged by human endeavor, constant in their movements, reliable in their appearance. They witnessed all that occurred below, the rise and fall of empires, the movement of peoples and goods, the slow accumulation of connections that bound the world into networks of relationship and exchange. The landscape settles into evening quiet. The heat of the day releases from the ground, creating subtle movements of air. Temperature begins to fall, though the stones still hold warmth, radiating heat accumulated during the long afternoon. Colors mute toward monochrome, the vivid golds and siennas fading toward gray and blue. There is a completeness to this moment, a sense of cycles continuing, of patterns that persist despite all change. The routes may have faded. The caravans ceased their movement. The great cities diminished or disappeared. But the fact of connection remains, written into the landscape, embedded in human culture, persisting in ways both visible and invisible. I remain here as light fades, as the pathway becomes less distinct, merging with the surrounding terrain. The boundaries between earth and sky soften in the dimming light. Everything becomes gentler, more diffuse. The hard edges of midday dissolve into evening's ambiguity. The wind continues, patient and persistent. It will outlast all human endeavor, all cities and routes, all empires and exchanges. It moves without purpose or memory, simply following the patterns created by temperature and terrain, carrying dust from one place to another, eroding and redistributing, participating in cycles that operate on timescales beyond human comprehension, and in this moment, standing where so many stood before, I am connected to all that history, all those who paused at this same spot, who looked at these same mountains, who felt this same wind. They are gone, but their passage created something that persists, a web of connections, a legacy of exchange, a demonstration that distance need not divide, that differences can coexist, that human beings are capable of reaching across vast spaces to touch one another's lives. The pathway fades into gathering dusk. The last light touches the mountain peaks, gilding them briefly before withdrawing. Darkness rises from the valleys, filling the low places first, gradually claiming all the landscape. The stars emerge one by one, ancient and familiar, marking the vault of heaven as they marked it for all those travelers, all those seekers, all those who dared the journey between worlds.